welcome you to our workshop. All right, so I'm just gonna make sure my beautiful other co-organizers, Natela and Agostino, are also here. Can you just let me know if you can hear me well, Natela or Agostino?
I can hear you.
Perfect.
Hi, everybody.
Great. We decided to put together a workshop after a few local meetings here close to Bay Area and Reno, and put together I think a great lineup of researchers from industry and academia to talk about practical issues in eye tracking. My name is Kamran Binaee. I'm here at the University of Nevada, Reno. Natela and Agostino, do you want to say a few words before I proceed to the next few slides?
My name is Natela, and I'm a scientist at the Smith Catterwell Eye Research Institute in San Francisco. Agostino,
do you want to say a few words?
Hi, everybody. Oh, let me turn on the video. Hi, everybody. I'm Agostino Gibaldi. I used to work at UC Berkeley. Now I'm at Magic Leap. I recently moved to academia. Sorry, but I'm babysitting. I will be done soon. Let's enjoy the workshop.
Sounds good. Our advisory committee are Dr. Paul McNeilage and Mark Lesquois, my PIs here at Reno, who helped us to put together the idea of this workshop together. Mark Pogan, if you are, I'm actually going to promote Pogan here. If you want to say a few words, please go ahead. I think you can now unmute yourself.
I'm looking forward to the presentations today. Got nothing else to say. Thank you very much, Cameron, for putting this all together. It was really largely his endeavor, and Natela and Agostino.
Thank you, folks. Pogan, can you checking whether your mic is on? If not, we can get back to you later. I guess we are super excited, as I'm sure you can guess. Before we move on, I just want to also thank our graduate students, volunteers, Christian, Barath, Ayush, and Rakshit to help us to put together this workshop. These are our attendees across the world. We are extremely excited, which was great to know we have so many participants for this workshop. And I guess from this point on, we are going to move toward our first keynote talk. Let me first stop sharing my screen here.
Should I share my screen, Kamran?
Yes, I think I want to go over one more. I'm sorry. Okay. Apologies, Kai. Let me just go over one more item before we jump into the keynote talk. So since this is a program in a glance, we're going to have keynote talks, 4 talk sessions. In between those sessions, we will have breaks. Except the first keynote talk, everything else will be recorded. You all have access to the Q&A underneath the Zoom panel. Feel free to post your questions. We will make sure to address them to our presenters. Toward the end, we will also have a Gather Town social hour after 2:30, because that will be midnight Central European time. So we put together another extended hour. If anyone else wants to hang out and have some more questions, by all means, please let us know. And we do also have a few more announcements for the potential for extending your work if you publish in this workshop as a journal under behavioral research methods, which Agostino, you can talk about it now if you want to. We can get back to the slides. Which one, what do you think? We can talk about it now, or we can address this later.
I would get back to it later if you don't mind.
Sounds
okay.
All right. So Just to explain a little bit more, we have a panel discussion about the practical issues, practical problems for large-scale eye tracking. Thanks again to our People Labs folks that joining us in order to be able to conduct this panel discussion, and also experts from academia. I will highly encourage you to join us for that session also. And then without further ado, I'm gonna hand it over to Agostino to introduce our keynote speaker, Kai Dierkes from People Labs.
Go straight into the first talk, which is Ergonomic Design Development of the Visual Experience Data Headset by Bharath Shankar and colleagues from the University of Nevada, Reno.
We might want to ask Kai to please stop sharing his screen, and then we can switch to Bharath, I guess.
I guess we're experiencing slight technical difficulties. Kai, are we able to unshare for him?
I've never tried that. Let's see. Oh, perfect.
Aha.
There we go.
Can everybody hear me?
Yes, I can.
Okay, cool. Thank you. Thank you, everybody, for coming to listen to my talk, which is a quick overview about the ergonomic design development for the visual experience database headset. Here's a quick outline of what I'm going to be going over today. I'll talk about what is VEDB, the Visual Experience Database. I'll give a quick outline of the hardware components we're using to collect data for this database. I'll go through the objectives and some of the tools we use to help build these headsets, and then I'll present the various head-mounted assemblies that we built, and then we'll revisit the objectives to see how well we've accomplished them. So first, what is VEDB? What is the Visual Experience Database? In a general sense, this is a set of recordings of natural behaviors in natural environments. You see, progress in both human visual neuroscience and computer vision has been limited by the availability of representative visual data. Most data sets of images and movies that exist currently don't show typical first-person visual experience. And so with the VEDB, we're in the process of collecting over 240 hours of first-person video complete with eye and head tracking. We're recording from a diverse set of people across 3 geographically distinct sites as they engage in common everyday activities. And using data from VEDB, we can address scientific questions from vision science and psychology fields. We can compute descriptive statistics of head and eye motion, various types of continuous low and mid-level image statistics, as well as stats about scene object context. I'll go through the hardware components that we use to collect data for VEDB. One of these is the Intel RealSense T265. This out-of-the-box head motion tracking camera system provides 6 degrees of freedom head position relative to the environment by fusing inertial and image sensor data streams. Our eye tracker of choice is the head-mounted pupil core system. It has a low mass, low profile frame, and the software side is open source, meaning we can customize and modify the code for our purposes. Now you'll notice pupil core has a world camera, but for this database, we needed higher quality images. We chose the FLIR Chameleon 3 camera as our world visual scene facing camera, as it has a wider FOV and higher spatial resolution than pupil core's world camera. When we put these hardware components together, we had a few objectives in mind. First and foremost, we need the systems to provide clean, low noise data. So we needed to think about factors that could affect the data quality, such as slippage of the hardware components, either relative to one another or relative to the wearer. We also thought about factors that could affect data flow as well. Another objective is that these head-mounted assemblies need to be easy to use. When worn, they shouldn't hinder any natural movement or make data collection impractical in any way. And third, the systems need to have a generally comfortable fit for a wide range of users. Since we're interested in first-person perspectives from multiple participants, we need these systems to be both easy to use and comfortable for those participants. We used a few design tools to kind of bring these headsets together. To design the pieces and parts that held together the hardware components in a stable frame, we used a free web-based CAD software called Tinkercad. And we printed and prototyped those parts on a 3D printer called the Creality Ender 3 Pro. What you can see here is a time lapse of a set of parts for a headset being printed out. We'll be able to see what these look like more closely in a few slides. Now I'll show you the various headsets that we've developed. One particular system is the head position only headset. This uses just the RealSense T265 to collect head position data. You only need the T265 hardware component if you're interested in head position data. The RealSense sits inside of this rectangular box mount and is held in place with 2 screws. This hinge cover opens and closes the image sensor view of the T265 for privacy during data recording sessions. This whole system connects to an elastic action camera head strap, similar to a GoPro headband, via this hinge piece that you see here. This system delivered very good data quality and was very stable and comfortable to be worn. Participants were able to collect and wear and collect data with the system for up to 5 hours. And with the cable secured to allow sufficient slack leading from the headset to the recording laptop, the system did not interfere with natural movements. We then sought to combine head position and eye tracking systems. We developed the positional head eye tracker, which uses both pupil core and the RealSense T265. Again, we have the familiar rectangular box mount, which the T265 sits in and is held in place with screws. And this whole array clips onto the top frame of the pupil core, as you see here. Now, despite the compact size of the T265, this added weight caused the frame to be front and top heavy. So we use sports glasses straps to keep the device on the head. The additional weight also bore down on the bridge of the nose. So we added some foam padding at the eye tracker's bridge piece. Despite these modifications, participants were only able to wear the device for about 15 minutes comfortably. The device did provide good data quality and did not impede natural movements. This is the first headset that we developed that integrated all of the hardware components that I presented earlier, the pupil core, the T265, and the FLIR. The RealSense sits in this bracket here. The pupil core frame clips into these claw brackets that you see here, and the FLIR camera sits on this mounting plate and is held in place with screws. All of these 3D printed pieces are clipped around a hard plastic headband, which you can see better here. I also want to bring your attention to the FLIR mount here. You'll notice that there's a number over here on the back, and that signifies the angle at which the downward angle pitch at which the camera is positioned. We needed to develop different angle mounts so that we could adjust the angle of the camera to effectively record the video action space as the variety of participants we have different heights and different natural head pitch positions just during natural behavior. Though this headset was successful in rigidly attaching all of the components to each other, several users reported that the system was uncomfortable. Some users had to position the headset in a somewhat awkward manner to get the eye cameras to observe the pupils. And the headset had to be significantly tightened onto the head to remain stable. This caused pressure at the forehead and back of the head areas, especially where those brackets were attached to the headband. The hard plastic headset proved to be somewhat of a hindrance as well for the variety of head shapes that we encountered. Data collection was difficult for people with more hair, wide head shapes, or even very small heads, such as heads of children. So we decided that a significant redesign was needed. So we took elements that worked from the head position only headset and VEDB V1 headset to arrive at this updated design. We did away with the hard plastic headband and used the elastic head harness from the head position only headset. And when we used that, we found that it had an improved fit for more head sizes, head shapes, hair mounts. The elastic head straps were also exhibited reduction in strain. It was reduced strain when wearing this compared to the hard plastic version 1 headset. And as you can see here, there are fewer parts to assemble. You just have the RealSense bracket here, the RealSense sits within here, and you have the same FLIR camera mount from version 1. And here you can actually see the headset in action and actually see all of the parts, how they all fit together. We evaluated the comfort between version 1 and version 2 headsets just using a survey. And despite the currently low sampling that we have for the version 2 headset, it does seem that the updates to the headset design are proving to be more comfortable, and it does seem that people can wear the device for longer as well. So how well did we accomplish our design objectives, the ones that I mentioned earlier? All of these systems provide clean, low noise data. The data quality from all of these systems is very good. There's very little slippage, interruption of data flow. All of these systems are relatively easy to use as long as the cables are secured in the back and allowed for enough slack. There's no hindrance for natural head motion, and there's very little that makes data collection impractical. And for the most part, these systems are generally comfortable and can be used for a wide range of users. I would like to thank everybody who's been a part of this project. The Visual Experience Database is a multi-site, multifaceted project that involves many people. So thank you, and thank you for listening.
Thank you, Rakshit. That was a great talk. There's a comment or a question from Anna in the Q&A. She says, super nice. Would have been lovely to have had that headset back when I recorded my data. Maybe I missed it, but how do you align the data streams? Do you use LSL?
I'm not familiar with exactly what LSL is. But the way we align data streams is we have a calibration and validation procedure that's fairly extensive. There's basically like a 5x5 calibration, a 4x4 validation procedure that we do at the start of the recording session and at regular intervals during the EDB recording sessions.
She's clarifying, LSL is lab streaming layer.
Lab streaming layer. No, we do not use lab streaming layer.
Okay. Thank you. And Craig is asking, is this data set going to be made available publicly?
Yes, the data set is going to be made available public soon. It might be I think we're in the process of kind of making the data in a publicly available state. We're still working on that. But yes, this database, the intent is for this to be a publicly available data set for people to be to use freely for research purposes.
Great. Thank you so much, Barath. That was a great talk. If I think we can move on to the next talk, integrating high fidelity eye, head, and world tracking in a wearable device by Vasha Dutel and colleagues from the School of Optometry and Vision Science at UC Berkeley. So Vasha, whenever you're ready.
Great, thanks so much. Can you see my presentation? Okay, wonderful. All right. So thank you so much. Thanks, everyone. My name is Vasha Dutel, and today I want to talk to you about a project we've been working on, designing a wearable and mobile device that can integrate high fidelity eye, head, and world tracking all together. Let's see if I can. Okay, so the motivation behind this is probably why most of you are already here. We're interested in taking the really great eye tracking technology that exists in the laboratory, and then we'd like to move it into the natural world. And the idea here is to be able to study the relationship between the human visual system and the natural environment that it involved in. And in particular, in our study, we're super interested in understanding the high spatial and temporal frequency components of the natural world. So we want to be able to record in high fidelity so that we can, as much as possible, match the high fidelity sensitivity that the human visual system has to the natural environment. And so a previous piece of work out of the lab that we're sort of basing this off of is the Boris head-mounted device. So this was is a head-mounted binocular eye tracker that was able to record environmental body, head, and eye motion in the natural environment. This device was optimized a little bit more for disparity statistics. So it had a binocular set of cameras. And because it was a couple years older, it uses grayscale images and records in a little bit lower spatial and temporal resolution that we'd like. And it uses an eye link, so it's a little bit bulky on the head. And so what we'd like to do is take advantage of the better sensor technology that's become available in the last couple of years in order to sort of improve upon this a bit. So this is the head-mounted device that we have been working on. It incorporates a high frame rate camera made by Zinnia. So that's here, the circle one. And we also use the Intel RealSense depth and RGB sensor. We have People Labs eye tracking binocular. And we also use two RealSense trackers, just like you heard about in the last talk. We have one on the head and one on the back to do head and body motion. All right, so I'll talk a little bit about the hardware in depth. So we use that Zinnia camera that I mentioned. So this is really our high spatial and temporal sensitivity camera for that high fidelity capture. So it records an 8-bit at 2K by 1.5K, and we can get 200 hertz out of it, which is really wonderful. So this is just a little bit of visualization of it. So you can see that it's quite small, which is wonderful. The lens that we have on it is actually as big as the camera itself. Pretty lightweight. So we get about 34 pixels per degree out of it based on the lens that we have. And then it uses this PCIe interface. So this ribbon cable shown on the bottom is going to this switch box, and we mount that on the back of the head, and that switch box converts into a PCIe signal that can go to the acquisition computer. And we save these frames in RAW format to avoid any compression artifacts. So the next sensor that we have on there is the D435i depth sensor. So that has an RGB stream at 60 hertz and a depth stream that we're able to run at 90 hertz, which is great. It's about half of the temporal frequency that we get out of our 200 hertz camera. We use the RGB stream as the world camera in pupil capture. And then we, excuse me, that should say depth saved in RAW. We save our depth information in RAW to avoid compression. Then the other sensor that we have on there is the T265, which you just heard about. We have one on the head, and then we have one on the back to get head and body motion. So this sensor combines two fisheye image sensors with an internal IMU, and that gives us visual inertial odometry, which is at 200 hertz again. Then we're using the pupil core eye tracking system. So binocular eye tracking, again, at 200 Hertz. The system is really lightweight, which is really great. And when we're using the pupil labs calibration, the accuracy of that is about 0.5 degree. Okay, so in order to collect all this data from these sensors, we designed and built an acquisition computer. So on the left here is kind of the insides of all of it. So it runs on DC power, so we can run it on batteries. It uses a mini ITX board, so you can see it's quite small. This is like a USB port sort of for scale. It has dual M2 support, so M2s were super important in order to be able to write to disk as fast as we needed to record when we're getting this data in from these high frame rate cameras. And then, as I mentioned, the Zimia camera uses a PCIe interface, and this is why we couldn't use a laptop like a lot of other people do, because we needed that PCIe input. And then a bunch of just USB ports, including USB-C for all our sensors. It has a HDMI, which we plug into a touch screen that we have mounted inside the casing of the computer. It has onboard Wi-Fi, which allows us to control the acquisition computer through remote desktop when we're mobile. We found that Intel i7-8700 has a low wattage requirements, which is perfect for battery, but also has the power of an i7, which allows us to save all that data. 32 gigs of RAM, some more USB ports, and then we also leave Ethernet exposed so that we can transfer the data off of the device, which was a surprising challenge that it actually took quite a long time to move all that data off of the computer after we were done, and then a DVI port so we can use a screen when we're not mobile. Okay. So as I mentioned, we run on DC power. So on the left here is a image of the power supply that we use for the computer. So this just allows us to use batteries. And then one thing that's kind of funny, we found that a really great solution for us for power were CPAP batteries. So these are these batteries meant for like a medical device, but they give us the voltage and the wattage that we needed in order to power this computer. And we can get about an hour of recording out of that, which is decent. Out of 2 of them. Okay, so then the full device together is shown here. So the helmet has 8 cameras on it alone. It weighs in at about just under 1.5 kilos. And then the backpack, which is shown here, inside the backpack, we have the computer, the batteries, and the second tracker that I mentioned, that weighs just under 4 kilos. So it's not the most lightweight, but I think it's not bad for how much data that we're collecting here. Okay, so then a word just on the software. So we designed everything to run inside of Pupil Capture. It's a really great interface. So we made everything as plugins. So for the Zimia camera, we designed some utility files and then a plugin that allows us to control the Zimia camera from Pupil Capture. So as you can see here, we can specify the serial number for the camera. We can preview the stream. We can adjust the gain using a settings YAML file. We also found it really important to be able to adjust the frame rate. So since we're running at 200 Hertz during calibration, we can reduce that frame rate and then we save space in recording. That was kind of our limiting factor. And then we can also toggle recording. We also wrote a couple plugins related to depth. So one was to be able to record depth in RAW instead of in the compressed MP4 format. We also wrote a plugin that allowed us to align the depth sensor to the RGB sensor for the RealSense camera online. We found that that reduced our frame rate a bit, so we ended up not using that, and then we do it offline by putting the stuff in a bag file and using the align function, and that allows us to align to the Zimia camera as well. We also designed plugins related to calibration. So we have a custom calibration routine, which you'll hear more from Agostino in a couple talks later today. So I'll leave him to talk about that. But then I wrote a cute little plugin that allows you to put a 9-point calibration target position over the world camera. So we have a handheld calibration target, and then we can direct the subject where to put that calibration target to get a 9-point. And then finally, we adapted some of the plugins from Hausemann et al. And those are just related to collecting data from the 2 trackers. We adjusted a little bit to be able to use both trackers at the same time along with the RGB camera. Okay, so data flow, as I've kind of alluded to, was a really big thing in this project. So from our Zimia camera, because we're recording in RAW and it's super high fidelity, the data rate coming in is 637 megabytes per second. So it's pretty fast. I mean, in 2 seconds, you're getting over a gigabyte, which is really, really a lot. And then when we recorded depth in RAW format, that also increased our data rate from the depth. So it's really quite a lot. The other sensors kind of really pale in comparison in terms of data. So this is why the M2s were super important, because it allows us to write as fast as we're recording and we don't fill up our RAM. We have 3 terabytes total, and that gives us about 70 minutes of data collection at full frame rate. We get a little bit more just because we lower to 30 frames per second for our calibration. And we have another external SSD that we can write to in case we run out of room. Okay, and then finally, ergonomics. You heard a little bit about really similar design considerations in the last talk. So these are kind of our solutions to these issues. So we designed this adjustable camera mount. So it's like a 3D printed mount, and we were able to put all of our cameras on it. And then we have these we have this system that allows us to adjust the camera entire mount as needed, and then secure it so we can adjust for like a near task versus a far task, for example. And then, so we also adapted the Pupil Labs eye trackers with a similar ball and socket mount that they have. I don't know why this isn't loading. Gosh, wish I had a photo. Anyway, I'll just tell you about it. So there we go. So we adapted it so that the eye cameras could connect to the helmet that we're using instead of with the nose piece, the glasses style. And that allowed us to easily adjust the cameras as needed for our setup. And then we also had mobility in mind. So as I mentioned, we can control the computer through remote desktop. So this is an example of when going mobile, we can control the acquisition computer through an iPad, through remote desktop. And that's an example of that. And then another design consideration we had was for these cables, we designed them so that they sort of went in a little bit of a loop here. And that loop allowed as the subject moved their head, the cable could kind of come in and out so that the person wasn't getting like pull on their head as they moved around. And you can see the other tracker there on the back in the backpack, as I mentioned. Okay, and then so just to give you an idea, this is somebody wearing our device, just walking through my house because it's COVID. And as you can see, we can record their eye position, and they're able to move freely throughout the environment with this device on them. All right, so then I think that's it. So thanks everybody so much for your attention. And then I'd like to thank everybody that contributed to this project, and especially Agostino, who was my partner in crime in this project. And thank you to my funding sources also. Thank you so much. I'll take any questions.
I can ask one if there's no question. I don't see any question on the list. Natela, do you mind if I ask the first question?
Go ahead.
So I love the setup. Thank you for the great talk. Quick question regarding the compression, because we did discuss this when we were collecting data. I'm guessing there should be playing with the CRF parameters and the FFmpeg features to get a good compression, but then don't lose a lot of visual features. Can you elaborate on that a little bit?
Yeah, definitely. Yeah, great question. And yeah, that is something that I was pretty hardline on this project, to not have any compression in it. And the reason was because for me, at least, the reason I was interested in this project was interested in studying the spatiotemporal statistics. So I wanted to do a bunch of Fourier transforms on the spatial and temporal on the video basically, and with the eye-mounted video. And so just for my purposes of why I wanted to collect this data set, it was important to me that there weren't any artifacts at all, because the readout for the data set in the end would be the Fourier transform, which would be really affected by that. But yeah, you're right. If that was not the goal, like, you could absolutely save a lot of you could get rid of a lot of these design considerations and not worry about it and make your life a lot easier. if you were able to compress it. I mean, you saw with the depth, for example, right? Like how big that got by recording it in RAW, and you could do the same thing for the high frame rate camera.
So we have some really great questions. I'm not sure if we'll get to all of them, but we'll start with the one in the chat. Barath asks, are you collecting only IMU data or both inertial and image from the T265 on the back?
Great question. Yeah, no image in this recording, just the IMU stuff, because we have plenty of recording from the images from the other cameras.
And Brian asks, how do you ensure synchronized data? Do you have a playback mechanism to play back all of the integrated data together?
Yeah, that's a great point. So yeah, we spent a lot of time just testing and making sure that the playback works. So let's see, I think most of these devices have internal clocks, and then we do, I think at the beginning with the Zimia camera in particular. So I think we let Pupil Labs take care of the synchronization with the other sensors, but with the Zimia one, I think we do a comparison of the internal Zimia clock to the computer clock in the beginning and at the end, and then we measure like how much those have drifted. And then we like interpolate in between, I think, but we did a lot of testing to make sure it's not more than a couple of frames off throughout like a couple minute recording session.
Thank you so much, Vasha. There are a few more questions, and perhaps since you're one of our panelists, those questions can come up then. But thank you so much for a great talk.
Yeah, thanks so much.
So our last but definitely not least talk in this session will be pupil tracking under direct sunlight. And it will be, the author on that is our very own Kamran Binaee from the University of Nevada, Reno, along with his colleagues. Take it away, Kamran.
Thank you. All right, so hopefully everyone can see my slides, right? Perfect. All right, so yeah, the title of this study is People Tracking Under Direct Sunlight, and I guess I'm already super excited because of the line of talks that we already saw. So I'm not going to go into too much detail about visual experience database, but just briefly, this is our setup as Barath showed in his beautiful slide, and we are collecting data over a wide range of different activities, environments, lighting conditions, and tasks. So I'm guessing that by now you're we are all pretty in agreement that there are going to be a large list of issues and problems for collecting such large-scale data sets. For instance, we spent a lot of time on figuring out what world camera performance do we want to achieve. We tried different options. We ended up using FLIR. Device ergonomy, which I think beautifully was explained by Barath. The head pose tracking, making sure that the head pose reported by T265 remains accurate throughout the data collection. Privacy and ethics, also another, I guess, active topic of these kinds of studies that we are facing these days more than before. But during this presentation, I'm only going to focus on our gaze tracking efforts, just to make sure that when we go outdoor, under different kinds of lighting conditions, we're going to have a consistent gaze tracking accuracy. More specifically, we're going to talk about eye image qualities and what kind of improvements can be applied to the eye image in order to get an accurate gaze estimation. In order to know which part of the pipeline is going to be troublesome or is going to be the bottleneck, let's just quickly go over the eye tracking pipeline. So as explained today, we start with pupil tracking, get an estimate of where the pupil is in the eye image. At the same time, we would need to track a target, a known target in the world camera, and depending on which kind of calibration, in this case 2D calibration, which can be simplified as a simple mapping or regression model between the points on eye camera coordinate system to the world camera coordinate system. or the more sophisticated one, which is referred to as 3D people tracking, here shown in people lab technique. No matter which of these techniques we are going to pick and use in our data set, which by the way, we are trying to include all of these different techniques in order to be able to have the versatility for the end user of the database. I guess we all agree that the first critical part is the quality of the eye images. That's where we get the most important failure or the most notable problem when we go outdoor. For instance, if we use default camera settings, we're going to end up with an image that looks like this, which, as you can see, it's not ideal at all. This problem has already been addressed and has been revisited in previous studies. For instance, Evans and Dr. Pels in 2012, they were using a positive science eye tracking in an outdoor environment, and also similar studies by John Mathis and Gegenfertner's lab. But all of these previous studies for outdoor eye tracking, they use shades in order to basically resolve the problem that I'm trying to talk about today. Using shades solves part of the problem, and I totally agree with that. But there's also some side effects to that. It puts some mechanical or ergonomic constraints for the way that you would want to design your headset. Another side effect of using shades is sometimes it creates some artificial or unnatural gaze behavior. For instance, participants looking underneath the shade in order to, for instance, perform a daily activity, which is not ideal. Therefore, we are trying to tackle this problem without using any shades. So more specifically, we are trying to answer two main questions here. What are the camera parameters that we can use in order to improve the image quality? And in order to explain that, let's just quickly revisit this so-called imaging chain that is happening in almost every cameras. In this case, People Labs eye camera. So we have this IR lens. We have a system lens to provide the images, and then we have this IR filter in order to remove any rays of light that are not in the spectrum of IR. And then we get a raw image out of the sensor where there can be some post-processing, onboard post-processing happening on the camera in order to improve this quality. More specifically, we're going to figure out what kind of post-processing parameters we can use to improve the quality of the image. In order to characterize the image quality, we have to have a metric. So for the quality metric, what we ended up deciding to use in this specific study is to use RITNet as our people segmentation technique, which is one of the most successful ones. And while we get a segmented regions of the eye, meaning pupil, iris, sclera, and also the skin, we would fit an ellipse to the pupil. And also we can do the same thing for iris. In this case, there's a good example of, okay, this is a good segmented region, pupil being in the center and then iris around it. And also another an example that is not a good fit. And what we are trying to say here is we use the residual error for ellipse fit as our quality metrics, as our image quality metric. And therefore, we're going to explore this space of parameters and find out which image setting is going to give us a more accurate estimation of the pupil. So we collected data in controlled and outdoor environment, meaning that our 6 subjects fixated at 5 different points in a known pattern while they are outdoor. And then from the list of possible parameters that we could choose, we narrowed down our search space over brightness, gamma, and sharpness. In a preliminary study, we investigated more parameters, but we found out that these 3 are the ones that are creating the most significant effect. Furthermore, we also tested under 4 different outdoor lighting conditions. In a day where it's gloomy or overcast, or it's cloudy, where the participants are facing the sun in an oblique direction, or when they are facing the sun in a direct direction, and also for indoor conditions. So basically, these are our different independent variables that we change when we're collecting controlled data. Here, I'm going to show you an example of what the images look like under these different settings. So every single column here is different brightness values, which is between 0 and -64. I think that's the full range of negative values that you can set for people eye camera. And also each row shows different gamma values, gamma being the famous stretching, intensity stretching function in order to make your different intensity of the images look separate for the purpose of segmentation. Okay, so basically that's one panel of the settings that you can get from the eye image while the participant is fixating at one of our fixation points. And also we repeated the same exact, actually before that, I just want to reemphasize that this is the default settings if we don't make any changes to the pupil camera parameters. We repeated the same procedure for 3 different sharpness values. So the question was whether if we increase or decrease the sharpness value, are we going to get a better estimate of the pupil under these different lighting conditions. So this is an example for one participant's data for indoor lighting condition. The same for shade, overcast, or gloomy, where it's not super bright. And then this is the sample image for one subject when they are facing the sun in an oblique direction. And finally, our last and probably the worst condition where we are basically left off with just a single pupil in the eye image. So these are basically the space that we searched for our 6 subjects worth of data. So in terms of the results, here I'm showing different lighting conditions in the x-axis, and on the y-axis is the residual ellipse fit error in pixel coordinates. That means lower the better. So that means, for instance, in this specific camera setting, we have a good time in terms of being able to fit in a confident ellipse to the pupil under oblique and direct sunlight, but not very much for the other 2 conditions. So basically, I'm going to show the same panel now over the different range of settings that I already explained in the previous slides. And then this is the whole range of our camera parameters that we saw before. There are a few points that we should take out of this first part of the study, and that is we might not end up having one single minimum for all of these conditions. Even for one of these, even if we can consider, for instance, shade condition, we can still pick this setting or this one or this one. There's no specific like one single minimum for the whole, and that could be because of the range of data collection and also the fact that there's a little bit of difference between how the pupil detection is being implemented. Therefore, we are saying that these are the range of these are the recommended ranges that we would want to use if we are going to use different if you're going to collect data under different lighting conditions. Another point that I want to make here is increasing the sharpness did not help from a certain range above, which I'm guessing is probably because introducing some speckle noise around the pupil, probably causing some difficulties for pupil detection purposes. So now we have optimized, if we can accept it's not an actual optimization happening here, but we have improved the camera settings. Let's test them in action. What we are going to do is we're going to use the eye camera settings, collect outdoor data, and then test the pupil detection accuracy with 3 different techniques. Pupil labs, this is the older version. This is not the 3D pupil tracking. I should say that. I'm guessing we will get more improved results as we implement the newer one. DPOG, which is another deep learning based technique for detecting the pupil position, and RIT-net. So basically what happened during the outdoor data collection is participants walked as they were trying to fix it on a certain point. And then we made sure that they are being exposed to different kinds of lighting conditions, in this case, direct and oblique sunlight. And then here's what we get for the confidence values reported from the pupil labs, shown in red, DPOG shown in blue, and RIT-net shown in green. So basically, DPOG and RITs are performing better, and their failed cases are also kind of happening around the same time. In general, DPOG provides a tighter distribution of confidence values. So What is next? Basically, we have improved the image quality, but still we haven't been able to finalize the gaze tracking. And the problem is we will probably need to do more contrast enhancement between iris and pupil. So for instance, DPOG assumes that this is the pupil because of the fact that the training set probably did not include these kinds of instances. Another typical problem is reflections and shadows of the world around the iris, so that it causes the pupil segmentation to not perform perfectly fine. And just to wrap up the last part of my talk, these problems of squinting and reflections have been reported in previous studies here shown in this panel. And we also do the same kind of observations in our data set as we are collecting more data outdoors. So that's, I believe, would be our kind of future direction. So in summary, we provided an improvement to eye camera settings. We tested these settings under by using DeepNet ellipse fits and pupil detection techniques. And for future works, what we are trying to do now is scaling develop this segment annotation tool, very inspired by DPOG package, so that we can basically now create our own annotated images, retrain the deep networks, and hopefully improve the quality of the pupil tracking techniques. Finally, I just want to thank my PIs, Mark Lesquois and Pogan or Paul McNeilich, with their great helps, a fantastic group of grads and undergrad students. And I'm gonna leave you all with this final slide of our data collection efforts. We'll be happy to take any questions.
Thanks, Kamran. This is a great talk. While people are thinking of their most important question, I have a question for you.
Please.
Have you guys looked at the opposite problem of not enough lighting?
Not enough lighting. Yes, we haven't done too much data collection at night, but the good thing about IR illumination and IR filter for the eye camera is because there's no IR light, the indoor setting usually works well for during the night data collection. But I would be a little bit doubtful to have a very strong argument on that because we haven't collected so much data at night.
So one thing to consider is the pupil size becomes very big, and then you have that iris pupil issue.
Yes.
And I was just wondering if you guys had looked at that.
Well, that's a good point.
Well, sorry, go ahead.
I was just going to say that's a good point. We have to definitely collect more data at night to figure out where we do see a difference in the performance. Well,
I want to thank you, Kamran, for this great talk, and I want to thank everybody else in the session, Vasha, Baras. These were really, really wonderful talks. And oh, wait, I think we got a question. We have one question, and then we need to take a little break. Have you done any collection with IR lights, such as when integrated with IR-based motion capture?
Oh, we haven't.
Indoors.
We haven't. So that means I'm guessing probably the interference between motion capture IR light sources and what happens with the pupil camera. No, we haven't, but that's a good one. Yeah.
Okay, I hand off the reins to Agostino for the next session, and let's everybody take a little computer plugging in break. Thank you. Thank you all. Good.
Sure. Sorry. Share my screen.
Linux will.
Okay. I lost you. Okay. So. Okay. Do you see it?
Yes. Okay. So let me first say one word about this session. So this session is going to be about calibration and error mitigation. This work is noise in machine sources of physical and Computational error in eye tracking with pupil core wearable eye tracking devices. Presented by Anka Belisar. Please, by all means, take it away.
Okay, thank you, Cameron. Hello, my name is Anka Belisar, and I'm a research engineer in Eye and Head Movement Laboratory under Dr. Natela Shanidze in the Smith Kettlewell Eye Research Institute.
Sorry, Anka, just to interrupt you quickly, your slides aren't currently shared. You're in the notes view, just so you know.
But I do have, okay. I don't know how to get
Yeah, I guess you're sharing the wrong window, I think. That sounds like it.
Okay, and stop share and share screen. And we do this. Is that better?
Perfect, yes.
Okay. Okay, sorry. So today I will present results from experiments that we designed in order to identify sources of physical and computation error in eye tracking with pupil core wearable eye tracker. First, I will present a series of experiments that will address noise introduced in the eye position measurements due to the eye camera movement relative to the world camera during a natural and a passive body movement test. Then I will show results of an experiment designed to answer questions related with the calibration process employed when using pupil core wearable eye tracker and the effect of each calibration type on the measurement error. I will conclude with the proposed correction method and its effect over the measurement data. We use in our lab the wearable eye tracker pupil core. The eye tracker is lightweight and easily adjustable for different face configuration, is portable, low cost, and the company offers access to the raw data and the source code. These features make this system very attractive for head-body movement studies in small laboratories as ours. The eye tracker has a set of 3 video cameras, one placed on the frame on the forehead and oriented forward to register where the wearer is looking in space, and 2 placed on extended arms oriented towards the eyes to record the pupil motion. We augmented our set with a 9-degree of freedom inertial measurement unit oriented the same way as the world camera. This addition allows the use of the head rotation information given by the IMU to relate the eye movements to the gravity and the global Earth coordinate system. So this is the IMU that we placed. During movement tasks, there is a possibility of sharp changes in accelerations, like heel strike during walking or studies of head impact during sports. The jerk of the motion can be transmitted along the body to the wearable eye tracker and introduce noise in the measurement. There are already known fixes that addresses frame slippage, such as letting the 3D eye models to adjust during the task. Some sources of noise, though, cannot be eliminated, but knowing the noise level can allow you to evaluate your measurements. We designed a small study to explore the eye camera's mobility during 2 motion tasks. One, a natural walking on a carpeted floor, and passive hip motion produced by a DOF reality motion simulation platform. For this experiment, we used a rigid foam head here with printed eyes that we call Joe. We placed the wearable eye tracker on its head and rigidly attached it with staples to prevent any slippage. We oriented the eye cameras so that the printed pupils can be detected by the device. Joe was held firmly in front of the human participant by the participant for both tasks. We compared the motion of Joe's printed pupils during the 2 tasks to the motion of the participant pupil. In panel A, we present, next one. Okay. In panel A, we present the measured normalized pupil position in the eye camera image. Joe's pupil motion is in brown, and the human participant is in blue. In panel B, we show the vertical linear acceleration of the head measured with the IMU. The acceleration of the foam head during walking while held in the arms was larger than that of the human head when the participant walked by herself. This can be due to the fact that we are better in stabilizing our head during walking, or the walking pattern changes when holding something in your hands. The displacement of the printed pupils represent eye camera motion. The data suggest that 36% of the recorded pupil motion can be due to eye camera motion in this task. During the passive heave movement task, the head motion was similar for the human participant and Joe, as seen in the panel D. During this task, the camera motion was 21% of the recorded pupil motion. And because the two head motions are similar, then we can say that that's much closer to reality. So now to calibration. The calibration process estimates the relative 3D orientation of the eye cameras to the world camera. There are different strategies that can be used: a set of fixed markers that usually encapsulate the area of interest placed at a similar viewing distance as during the task, a single marker that can be moved while the subject fixates it, or a fixed single marker that is fixated during head motion. Is any one more appropriate for a given task? Does a more refined calibration grid increase accuracy? To evaluate that, we perform two sets of experiments, first with the head restrained, and then we repeat it with the head unrestrained, but instructing the participant to keep the head as still as possible during the static tasks. We performed 5 calibrations, 4 with a fixed set of markers in different configurations, a 5-point grid similar with the screen calibration offered in the pupil capture software, a sparse 9-point grid, a more dense grid of 13 points that we usually use in our lab as validation set, a dense and small 9-point star grid centered, and for the head unconstrained condition, we added one involving head motion while fixating a static marker. The head movement was formed by 4 right-left rotations in yaw and 4 up-down rotations in pitch, and we call this VOR calibration. We calculated the calibration matrices for each set using pupil player. Then we evaluated the calibrations on a validation set comprised of 25 markers locations. We calculated the static errors on all 25 points on a subset of 9 points, a 5-point, 13-point, the 9-point star, and all the inner, the 17 inner points to see if there is any difference in accuracy for each calibration for different types of visual tasks and resolutions. Additionally, we evaluated each calibration on data collected during 2 sets of 20 horizontal saccades of 4-degree and 10-degree size. And as I mentioned before, we performed all these tasks first with the head restrained, no VR calibration during this condition, and then with the head unrestrained. In the head unconstrained condition, we evaluated each calibration on the angular VOR data. During fixation of a static marker while rotating the head, the eyes are compensating for the head motion by moving in the opposite direction to keep the image static on the fovea. This effect is a result of the angular vestibulo-ocular reflex, or AVR. During the AVR at far viewing distances, the eyes compensate almost completely the head rotation in people without visual or vestibular impairments. We wanted to see if the choice of calibration affects the gain of AVR in our control participant. So based on viewing and interocular distance, we estimated the visual angle between the gaze ray and normal to the monitor when the eyes verge on any marker presented at 180 centimeters away. We consider these angles the ground truth. And as we see, we build a map where we have the horizontal visual angle and the vertical visual angle. And we here, for example, we show where the markers, what would be the correct angles, visual angles when you, for each eye, when you verge on the markers. Okay, so then we evaluated the measured visual angles. So I call it here alpha prime. And you see them with the empty circles here on the map versus the ground truth set. And this is how I calculate the static errors. For the saccade data, we calculate the saccade amplitude as the angle between the average gaze vectors measured during pre and post saccade fixations. So here we have this angle. Then the absolute static error. So as you see, there are differences between the measured and the ground truth. The absolute static errors can be reduced by applying a homography over the gaze data. A homography is a geometric spatial transformation map. We implemented a local weighted mean homography using a FitGeoTrans function in MATLAB on a 13 points validation set. We used that homography to correct the gazes during the 25-point validation set, during the saccade task, and during AVOR. We evaluated the errors similarly as before. And now we're going to the results for the absolute static errors. So here it's going to be a very heavy a graph. So I'm going to try first to explain. So here we have the data for the right eye, I0, on the horizontal direction. So in the first, in the left side of the graph for the head unrestrained condition, and in the right side, we have the data for the head fixed. We evaluated the errors for each calibration. So the colors are for each calibration, like the 5-point grid, the 9-point grid, the 13-point grid, the star, and here in unrestrained condition, the AVOR. While here, as you see, for the head fixed, we don't have the AVOR. And we evaluated the errors as for all the points, the 25 points, for a subset of 5 points, of 13 points, and the star. So as you see in this graph, there was no significant, even though the star looks that it's clearly off. However, when we did the stats, there was no significant effect of head condition, restrained versus unrestrained, or calibration strategy used. Okay, now is the bigger graph. So here we added the vertical direction and the other eye. So when we do that and we look at the data overall, we see that the results look similar. Then we added the errors after the homography is used. So after we correct the gaze, and then we see that the homography correction reduces the absolute static errors, even though significance was not always achieved. The 9-pore star, as you see, the brown, okay, produces the largest errors. More interestingly, the error calculated on here on a similar shape validation subset was the largest comparing to the other calibrations, showing that that it doesn't matter how what's the resolution of the calibration markers when you present it during the calibration. Also, the data shows that any given calibration is good enough if So now we go to the saccades. So we estimated the error in the saccade, the amplitude. So as I told you, we have a 10 and a 4-degree saccades. In the top, we present the small saccade, the 4-degree saccades, and we measured with each calibration, and then after the homography is applied. So as you see, and that's for, I think this is the right eye and this is the left eye. And you see that, for example, the measured calibration for the 4 degrees in the horizontal direction is clearly overestimates. So it's a 6 degrees, while actually the saccade was a 4-degree saccade. The other eye though is doing is better. It's around the 4 degrees. So the size of the horizontal saccades are slightly overestimated with each calibration. Additionally, the homography correction did not improve the error in saccade amplitude. So as you see, it didn't come down for the right eye. There is also a large difference in saccade amplitude between eyes. The right eye has larger saccade amplitudes than the left eye, with the left eye closer to the ground truth. By looking at the eyeball position in the eye camera, in this set of recording, the right eye 3D model is 42 millimeters from the eye camera, while the left eye is 37 millimeters. So we'll see if, one of the idea is that this actually might affect the scale. Now let's go to the AVR data. So I brought back.
Sorry, Anka, just 1 minute to the end of it. Thank you.
Oh, okay. So I guess I'm gonna skip the AVR data just because we are in a hurry, and I'm going to the end. So looking at how the errors actually, what's the difference between the measured visual angle and the one that actually should have been. Then looking at the direction of that, you can see actually that what actually is happening. And what's happening is that the calibration process, the optimization algorithm is underestimating the viewing distance. And it gives you the gaze point closer than the reality. So in conclusion, although the gaze point estimates can appear accurate in the 2D scene camera image, its depth is highly underestimated and must be corrected. The calibration process does not affect eye movement scaling. Most probably, the scaling is related with the distance of the estimated 3D eye model position relative to the eye camera. Using a homography, the underestimation of the viewing distance can be corrected, but it can increase scaling error. And I want to thank my colleagues, Natela, Shanidze, and Kate Agatos. And I also would like to thank James Kaufman and Kamran Binaee for advice on homography implementation. And this research was funded by NEI. And thank you, and please feel free to ask any questions.
Thank you very much, Anka. This was a great talk. I have a lot of questions. We have one actually from Kenan, but for the sake of time, I'm so sorry, but we have to move on to the next talk by Agostino. But I will promise, hopefully Anka will be around during the social hour so that we can go over the questions.
Sure.
Thank you so much. This was a great talk. I have a lot of questions. You know that this is exactly our problem. So hopefully we'll talk about it more.
Yeah, thank you.
Thank you. All right. So our next talk or final talk of this session is solving parallax error for 3D eye tracking by Agostino Gibaldi. Please take it over.
So sorry for that. Can you see the screen?
Yes.
Okay. So let's start. Thank you for being here today. Today I will talk about possible ways to solve parallax error for 3D eye tracking. The recent years have seen, as you hopefully know, a widespread of head-mounted eye tracking technology for measuring features like oculomotor behavior, attention in the natural environment. So, different solutions have been proposed from custom handmade devices, which might seem a little clunky and uncomfortable, but they definitely do the job. And then there are also high-end commercial devices that are becoming incredibly portable, lightweight, and comfortable, like the Glasses 3 from Tobii, the Viewpoint glasses, and what we have seen in the keynote, the Pupil Labs Invisible, and they basically look like standard sunglasses. Anyway, sorry. As Kai summarized in his talk, in designing algorithms for eye tracking in the natural environment, there are some characteristics that have to be taken into account that are pretty much different from what might happen in a controlled and structured lab setup. We commonly do 2 to 3 fixations per second while scanning our visual environment. And at each fixation, the fixation changes continuously. So what is required to get reliable and robust gaze data? Sorry, let me turn on the laser pointer. Where is the laser pointer? There is no laser pointer. Anyway, not a problem. In a lab setup, usually the calibration of the eye tracker is performed on a display screen that is placed at a specific distance. Then in the eye image, the pupil is segmented with some algorithms, and this position is mapped to a pixel position in the scene camera image, which corresponds, if you did a good calibration, to the position of the fixation target. But what happens if you want to use the device in the unstructured environment? The calibration screen would not be there anymore. And the target, the object of interest, could be at a different distance, for instance, as shown here, farther away. So if the object of interest would move, let's say, along the line of sight, the eye does not move as well, and the pupil segment is found at the same position, so the measured gaze is unchanged. But the object of interest is projected at a different location in the scene camera image, so there is a mismatch between the measured gaze and the actual gaze direction. This, of course, happens also if the object of interest is nearer than the calibration distance. So, what do we need to get rid of this dependence on calibration distance to obtain reliable gaze measurements? We need to know 2 pieces of information. First, the 3D structure of the environment, and specifically the 3D structure of the environment around the fixation point. And second, the transformation between the camera reference frame and the eye reference frame. In this way, we could perform an actual 3D calibration where pupil position is mapped to the actual gaze direction rather than pixel in the scene camera image, so that we can compute the fixation point position in the 3D space, and knowing the transformation between eyes and camera, we can reproject the fixation point to the scene camera image. In this way, we can correct our gaze measurement. So here, I will present a possible implementation of this method. That's what we did. At Banks Lab, we developed this device, which is made of a binocular eye tracker, the iLink 2, together with a custom stereo sync camera placed on the head of the subject in order to compute the depth of the 3D structure of the scene. The calibration setup is the complex part of this device. It is laid out so that the subject is sitting on a bite bar that not just prevents movement of the head, but also is able to accurately place the subject aligned with the center of the screen and at a specific distance from the screen. In this way, also size and position of the screen are known with respect to the bite bar and subject position. Then the subject performs standard 13 points calibration provided by iLink, and iLink returns the pixel position of the fixation point on a screen for each eye with quite decent accuracy, usually smaller than 0.5 degrees. So since the geometry of the setup is known and calibrated, a pixel position can be transformed directly into a gaze direction, azimuth and elevation for each eye. Next, the subject is also positioned on the bite bar so that the stereo sync camera is able to frame the whole calibration screen. So we put on the screen a calibration pattern in order to compute the sync camera position with respect to the screen, the pose of the camera with respect to the screen. So now, since the subject position with respect to the screen is known, this allows to work out the transformation from the sync camera to the eye reference frame, which is what we was aiming for. Now imagine that the subject is no more on the bite bar, but is free to move in the environment. It is possible to use data from the stereo sync camera to reconstruct the 3D structure of the scene and to put it in the eye reference frame. Then we can compute the gaze direction by the let's say the position of the fixation point for each eye on the virtual, because it's no more there, on the virtual calibration screen. And from these two gaze directions, we can compute the cyclopean gaze direction. Note that this method is able to correct for likely errors in gaze emergence measurement that can originate from the limited eye tracking accuracy, 0.5 degrees. In fact, it is even if the optical rays are not intersecting and they are not intersecting on the object of interest, it is possible to still compute the binocular line of sight as the line passing through the cyclopean point of the head and the best intersection of the two eyes gazes. So this is an example of the post-processing. The video is not starting. Come on. Sorry. Why? Okay. On the left, you see the scene camera image that is used to reconstruct the scene depth. And data from the eye tracker are used to reproject the scene to two virtual cameras representing the left and right eyes, but also to compute depth corresponding to the actual fixation point of the subject. Note that in our procedure, calibration is followed by the task and then by a validation. The average accuracy that we obtained in the validation is 0.71 degrees with a standard deviation of 0.14, which is pretty decent. But also note that about 1/3 of the trials were discarded at validation because the error measured during the validation was too high, probably due to the device slippage. We used the device with 4 subjects that performed 6 tasks in the natural environment, tasks designed to the action and different fixation distances, from making a sandwich to having a walk on campus. And this is a summary that the data we obtained. We were able to measure the average retinal disparity experienced by people in the natural environment, their average gaze direction, and fixation distance. These data are available, have been recently made available in a database, the Boris database, which is free to use for research. So, a brief presentation of the ongoing work. You've already seen a presentation by Vasha. This device, with Vasha, we started a project to measure spatial and temporal frequencies of the visual environment. So this device was not performant enough for the task, and we decided to re-engineer it, specifically with the aim of a scene camera going at 200 frames per second to get a good sense of temporal frequency. And we were also trying to make it lightweight and comfortable. So we were aiming to design similar to this, taking advantage of the style proposed by Pupil Labs. And what you've seen, this is the device that we managed to build, which is other than lightweight and comfortable, but still it's not bad, and it definitely is able to provide huge amount of wonderful data. Apart, we are focusing pretty much for this device. As you can imagine, it is difficult to bring the calibration screen around to make the calibration on site, which would make the usage of the device much easier. So we implemented a procedure that is able to exploit the depth camera and the handheld target from Pupil Labs to recover the 3D position of the eyes in camera coordinate. This is ongoing work, so I'm not saying much more than this, other than it is working pretty well. That's what it seems. So stay tuned, and you will hopefully see more. Briefly, some conclusion. So gaze measurements in the natural environments, in order to solve for parallax error, require to measure the 3D structure of the scene and to know the geometry of the scene camera with respect to the eye, to the eyes. The geometry of the scene camera and the eye plant can be obtained with custom lab setups to calibrate the tracker, but they are other than user-friendly. At least I'm talking about what we were able to implement. And it is not possible to move the setup on site to perform a quick calibration and repeat it over time. So portable and user-friendly methods should be implemented to enable rapid on-site calibration. Thanks to Natela, who has been a wonderful partner, crime partner on this project, and to Marty Banks, my PI, who provided a lot of help as well. And thank you for the attention.
Thank you so much, Agostino. This is great. We don't have any questions in the Q&A. We are 7-8 minutes behind. I'm going to ask very quick question and then move on to Scott's presentation. Is there any specific dependency on the periphery? If you go from center to the peripheral field of view, the parallax correction, does it improve? You might have said it in the talk, but I missed that.
I didn't say it.
Okay.
If you have rectified images from the same camera, eccentricity should not matter.
Gotcha.
Yep.
Perfect. Thanks again, Agostino, for the great presentation and great visualizations. We will move on to the last talk of this session. Scott, if you are around, which I can see you.
I'm here.
Perfect. Algo, do you mind if you
sorry.
Stop sharing, and then we can move on to. So the last talk is titled Sub-centimeter 3D gaze vector accuracy on real-world tasks and investigation of eye and motion capture calibration routines by Scott Stone. Please take it away.
Yes, I'm assuming everybody can see my screen. If you can't, just yell at me. Yeah, so thank you so much. So today I'm going to be talking about some of the work we've been doing in the lab for the past couple of years on the generation of 3D gaze vectors and their accuracy and performance on real-world tasks. And so before I talk about the experiment that we ran, I need to talk a little bit about eye and motion tracking in general. And something that we've noticed pretty early on is that few standardized protocols seem to exist around the collection and analysis of these kinds of data. And when we published a study a few years ago, we noticed that after the fact, we had to make some assumptions. And these assumptions around things like the eye data, which kind of eye data should we be using? Should we be using data from the left or the right eye or both, or some kind of hybrid approach? Which kind of calibration routine should we be using to co-register pupil position to 3D space? And finally, something I came up a little bit later on was what kind of coordinate system would work best for our given use case. And so in the lab, we have a few tasks, and the one I'm showing here is a pass the box transfer task. So if there's any Canadians in here, you probably recognize the Kraft Dinner brand. And what this task is you just pick up the box of pasta and move it between several different locations. And we just kit them up with eye tracking and motion capture equipment. And the task isn't supposed to be hard. It's just a very standardized and easy to deploy task for many of our different experiments that we run. And so when we started to collect data for this, our next experiment, we had a couple of objectives in mind. And the first being what combination of eye data, coordinate system, and calibration routine is going to generate the best gaze vector? And secondly, how do we actually measure the best gaze vector? Like, what does that actually mean? And so we have a piece of software in the lab that we've been developing for the better part of 10 years called the Gaze and Movement Analysis Tool. And basically what we can do with it is we can take data that looks like this, where we can take our motion capture and our eye tracking data. And this is pretty impenetrable to actually assess any kind of meaning out of this. And we can convert it into more friendly formats that look something like this. And one of the key points that I want to make about the Gamma software is that all of this stuff is done automatically. We don't like to do manual labor in the lab. And so all of these measurements that we can calculate and things like gaze vectors, we can calculate all of these automatically and systematically. So when we started to collect data, we had to make some decisions around the equipment we wanted to use. So naturally, we settled on the Pupil Labs Core headset, which I'm sure everybody here realizes is an excellent eye tracker, collects data at 200 hertz. We have an OptiTrack Prime 13W system in the lab that we use. And we wanted to come up with a sort of a blocked routine where we can complete 3 of each of our calibration routines that we came up with that I'll get into in just a second. And we wanted to complete 20 of those pass-the-box task trials, as well as 3 validation trials. And I'm going to explain what I mean by calibration and validation here in just a second. And so when we collected data, it looked something like this, where we would have our 4 different calibration routines, and then we would sprinkle in a validation trial in our first calibration block. We would collect the first 10 trials of our pass-the-box task. So they just move that pass-the-box around. Then we do our second calibration block, where we do the same calibration routines, just in a jumbled order. And then we sprinkle in a validation in there. We do the last 10 of our pass-the-box trials. And then we finish off with a final calibration block where again, we do the same calibrations, just in a different order. And so I showed you earlier the pasta box task that we do, which involves picking up a box of pasta and moving it around. And the problem with doing a task like that and analyzing it is we don't have any idea where the participants' eyes are looking at any particular time while they're completing the task. And so what we did was we came up with this validation task where we give an auditory cue to tell the participant to look at each of these 5 different locations for a set amount of time. And this just allows us to know exactly when and where the participant is looking at various points during the experiment. We came up with 4 different calibration routines. The first one here up in the top left, these are all playing at 2x speed. So these people don't actually move this fast. So the first one in the top left here is called the experimenter sweep. What we do is the experimenter will hold the wand, this calibration wand here, move it through space in kind of a zigzagging like S-shaped curve. And then we move it through the 3 different dimensions. So we go left to right, up to down, and forward to back to just capture all 3 of the different dimensions. The second kind of calibration we came up with is called the self sweep. It's actually identical in nature to the experimenter sweep, but the key difference being that the participant is the one who's holding it and moving the wand. So the actual routine itself is identical. We had this idea that with this paint calibration that maybe it makes sense to collect a lot of data in the areas we know that the user is going to be interacting with. And so what we do here is we paint these small volumes at these various locations that we know are going to be relevant during the passive box trials. So we just spend some time here and then the user just fixates on the tip of the wand. And finally, the stationary, the stationary calibration routine we came up with. Sorry, I don't know why I keep pressing that button. We fix the wand to the apparatus, and then we have the user kind of do a cross motion while fixating on the tip. So they look up, they look down, they look left, they look right. And then we have them do these sort of head swirling motions while maintaining fixation. So it's kind of like a vestibulo-ocular reflex if anybody in here is familiar with that. And so to get a sense of what the pupil data looks like, if we just track it over time. So this is just some pupil data that came out of one of the eyes. And you can see that the experimenter and self-sweep data looks relatively similar to one another, which makes sense because they're the same routine. The paint data, you can see some nice little clusters here where they were paying attention to various areas. And for the stationary, you get this really nice cross and these nice like head swirly or these swirling motions here. And so from this, we wanted to build some gaze vectors out of this. And to be exact, we wanted to build 72 gaze vectors. And so to get to 72 gaze vectors per data set that we collected or per trial, we took a look at the different kinds of eye data we can use. So we have data from both eyes. We can just use from the left or just from the right. So that's our first 3 factors. We, of course, have 4 calibration routines that I just showed you. We repeated them 3 times. And then we had 2 different coordinate systems. And I'm going to get into what I mean by this in the next slide. And in order to make all 72 of these gaze vectors, we just fit a linear model in MATLAB using the fit-LM function with the quadratic option along each of the coordinates. And so what do I mean by this Cartesian and spherical coordinate systems? Well, when we use a Cartesian system, we get a measurement of depth. And it turns out that, for one, we don't really care about depth for our experiment. And 2, the measurement of depth that we seem to get is noisy. And with the Cartesian system, the problem is that it kind of bleeds into all of the dimensions, just depending on how the user is situated in the environment. We can kind of get rid of this by using a spherical coordinate system, which constrains depth to a single coordinate. And so when we train our models, we can just exclude this row coordinate from our models, so we no longer have any of that noisy depth information embedded in our data. So when we start to look at the performance of the data, when we test our gaze vectors on calibration data sets, what I'm showing you here is a guy here. He has 72 gaze vectors shooting out of the front of his head. This is all generated in the Gamma software. And the more yellow the gaze vector is, the closer it is to 0 error, so that is closer to the tip of the wand. And the more blue it is, the worse performing it is. And what we can do is we can take the average error of the gaze vector's performance over the course of the entire data set, so over a full minute or so of data. And then for validation data, it's a little bit different. We don't actually want to assess it over the entire course of the data. We only care about the performance at specific locations. And so we actually have 5 different locations here that we cue the user to look at. And what we can do is we can find a period of when their eye velocities tend to stabilize. And from that, we can generate the gaze vectors for about 1 second of data and take what the error looks like at each of these locations relative to where they should be looking at these markers. And finally, when we look at task data, so this is like real world task data, what we can do is it's a little bit more tricky because we don't know where they're looking, and we don't control for anything in this case, but we can cheat a little bit in that we know something about human behavior. We know that when people pick up objects or set them down, they tend to look at them. And so what we can do is we can use gamma to track the velocity of the object that they're using and just look a little bit before that and see where their gaze vector is relative to the past box and calculate our error based on that. So for results, so what did we actually find? So I'm going to talk about the coordinate system findings first. So along the x-axis here on all of these graphs, I have the spherical versus the Cartesian coordinate systems, and then I have the 3 data sets here: calibration, validation, and task. And along the y-axis is just the error in number of millimeters that we calculated. And so what I think is pretty obvious here is that the spherical coordinate system seems to be outperforming the Cartesian coordinate system. And one of the reasons we think this might be is because we're not embedding that noisy depth signal in our data any longer. We can simply constrain it and not train it into our models. When we start to look at location data, and when we're looking at location data, we can only look at the validation and the task data. Something that we notice right away is that when they're looking at this side cart location, so the cart that's just sitting beside them, they actually get a lot worse performance. And we think that this performance is probably coming from the fact that they have to turn their head. And when they do so, they get a roughly 3 centimeter error added onto their gaze vector errors. But interestingly, we can actually also achieve sub-centimeter performance when looking relatively straight ahead. So when looking at these neutral and these blue shelf locations. And so this is actually really promising, and it tells us that we can actually get pretty decent performance sub-centimeter on a real world task. And to kind of suss out what kind of role does the eye data play when we're training these models and assessing the error, something that we found is that using data from both eyes is not universally the best. Initially, we thought it made sense to use data from both eyes because we have more data that we're throwing at the model. But in fact, what we actually see is when we're looking at the side cart location, we see that data from just a single eye, and in this case, the left eye, actually outperforms using data from both eyes or just the right eye. And after hearing that talk from Kai this morning, I'm beginning to have some thoughts about why that might be in terms of the left eye performance. And finally, we wanted to see what kind of calibration makes the most sense to be using in a task like this. And so when we take a look at our calibration routines tested on calibration data, we do see a main effect of the calibration type. We're tempted to say, oh, it looks like the stationary model, performs better than everything else, and the paint seems to be performing worse. But when we start to look at this in the context of more ecologically valid data, such as the validation or the task data sets, we don't see a main effect anymore. And in fact, they all seem to be performing relatively well. And so maybe it's less important about picking and choosing what kind of calibration routines you do and making sure that you're testing on the appropriate data. And so what's the take home? What's the point of this talk? So I just wanted to share this as some things that we've learned in terms of better analysis practices that might be useful. So number one, I think that using a spherical over a Cartesian coordinate system works really well for us. We don't care about the depth information, but even if you do care about the depth information, you can still use it. We just don't use it for our study. Using data from both of your eyes is not universally the best thing to do. And in fact, sometimes it makes sense to use data from a single eye, and perhaps dynamically to switch between the eyes might be a nice thing to do, depending on the context of the task. You should assess your gaze vector performance on data that you care about. It only makes sense to test it on data where you care about the actual performance. If it's on an ecologically valid task, that's different than testing it on abstract performance when you're trying to track the head rotating in a VOR motion. And finally, the calibration routine that you use may actually be less important. Maybe it just makes sense to just do a general routine where any of the ones that we suggested here might actually be useful. And so with that, thank you so much. I'll be happy to take any questions if we have time. But if not, feel free to reach out to me. My email's down here, and feel free to follow me on Twitter or chat with me on there. Thanks.
Great, thank you, Scott. This is a fantastic talk with a lot of awesome visualizations. I know Mark has a question. Mark, do you want to ask the question, or I can ask it for you?
Sure, I can ask. For the paint condition, that's a really interesting way to go about calibrating. How did the subject position their head during the paint condition? How are they instructed to position their head?
Position their head. So they just stand. There's no specific instructions given to them at all.
So
they're standing Sorry?
They sort of put their head wherever they would naturally to look at that location?
Yeah. Yeah, we
Okay.
don't restrict their movement at all.
And then another question from Canon: do you think ocular dominance might be the cause of the performance difference between left and right eyes?
I don't think that's the case, because this is we see this interaction across all of the participants. So that could be the case if the participants in general have a left dominant eye. I do think it might actually be more hardware related after hearing Kai's talk this morning. It is entirely possible, but that's not something we've really looked at.
Great, awesome. We are a little bit behind, but I want to make sure we cover Kenan's question for Anka's presentation. Anka, if you're around and if you're available, we can get back to Kenan's question now, where he was asking about, do you have a suggestion for adjusting the underestimated point of convergence? Maybe you can address that question now.
Yeah, so as we came with that idea of the homography, like applying and correcting with using a homography, and pretty much helps with the convergence, like with the adjusting for the viewing distance. That's how it corrects the errors. But in my introduce, so that's where it's a little bit unclear to me, and I still need to do a lot more experiments to figure out if affects the scaling, because the scaling of motion. So if you're interested, as we are interested in, like the cut size, or for example the gain during AVOR, then that if that's important to you, I guess you don't care so much about maybe viewing distance. So you kind of have to choose what you're interested in. But it's true, if you're interested in vergence of the eyes or some things like that, then you might want to use the homography to adjust for the viewing distance. So you have to kind of pick and choose depending on what task you do.
Thank you. I think this question is for Scott. Wait, I was gonna answer the question. Sorry. Nicholas asked something.
Was it about gamma?
I think so, yeah.
Yeah, I just typed an answer to that. Yeah. So
Perfect.
Gamma is not currently available for use. But stay tuned. If you do have some specific questions or a specific use case with Gamma, feel free to reach out to me or any of the other co-authors on this paper. But we're not currently making it available because it is kind of it's a very much in-house software.
Perfect, thank you. I guess now we can move on to our panel discussion. We kind of sacrificed a 5 minutes break. Apologies for everyone. I guess if you all agree, we can move on to our panel discussion. Natela, please feel free to take it away.
Sorry about that. I'm juggling a lot of windows here. Yeah, so we're very excited to introduce our panelists for the panel discussion on experience-based ideas for challenges in head-free eye tracking. And we tried to make the panel kind of a combination of individuals with industry experience and research experience and both sets of experiences. So today we have Moritz Kastner, Kai Durkes, Mark Thompson, Marcus Nystrom, Brian Sullivan, and Vasha Dutel. And please, each one of you, if you could take a moment to just introduce yourselves a little bit before we start the panel, that would be great. Thanks so much.
I just want to add one more point. Sorry, as folks on the panelists can start introducing themselves, I have to bring the rest of our panelists to the panel so that they can have their mic open and talk. As we speak, I'm going to do that right now. Yeah.
And while Kamran is doing that, for any of you who haven't figured out Q&A yet, if you have a question for our panelists, you can go ahead and type it into the Q&A box, or if you want to ask it with your voice, you can go ahead and raise your hand and we will try to make that technology work as well. So again, thanks so much to our panelists for joining us here today. Kai, do you want to start since you're already here?
Yeah, I can start. Yeah, so my name is Kai Dirkes. I'm the lead R&D engineer at Pupil Labs. And yeah, I'm happy to be on this panel. Who wants to go next?
Marcus, do you want to go next?
Hi everyone. I'm Marcus Nyström. I'm work at a place called Lund University Humanities Lab in Lund, Sweden, where we work and have been doing for a long time with many things related to eye tracking and eye movements.
Great, thanks. And Mark?
Yeah, hi. I'm also happy to be here. I'm Mark Thompson, and I'm a product manager at Pupil Labs.
And Brian?
Hi, yeah, thank you for organizing the workshop. Yeah, my name's Brian Sullivan. I have a background in psychology, studying human eye movements in natural tests. I've been doing that for about the past 20 years, and I'm currently at the University of Bristol in the School of Psychology. And I've done a fair amount of stuff with mobile eye tracking, so very interested to hear what we'll discuss today.
Thanks, Brian. And Moritz?
Yeah. Hi, I'm Moritz Kessner. I'm one of the founders of Pupil Labs, and I'm here with my two colleagues. I'm very happy to attend the panel.
Great. And I think our last panelist is Vasha, last but definitely not least.
Hey, everybody. Thanks for having me. My name is Vasha Dutel. I'm a grad student at UC Berkeley, and my thesis project has been on mobile eye tracking, you probably heard about earlier. And I'm grateful to be here and looking forward to learning and hearing all your questions.
So I should say that, thank you, Vasha. I should say that we have collected some questions ahead of time that we will ask, but we also encourage you to go ahead and ask questions live. Obviously, we've had some great talks that might have made you think of a few more questions. And Kamran, I think there were a few questions you were saving from previous talks that you wanted to include. Do you want to start there?
I think we addressed them, but I'm going to ask for help from the audience. If we missed any question, please raise your hand and we can address them now. I guess we did cover them, if I'm not wrong.
Okay, if your question was missed, please do ask it again. There's a lot of windows we're currently juggling between. So I guess if I will start with some questions. This is a question that someone asked for the whole panel. Can any of you talk about the future of machine learning in eye tracking on both the data collection side and the data analysis side, and where you see that going?
So,
and
I don't know, maybe
you know, go ahead.
I know somebody starts machine learning and eye tracking. So one thing that I find interesting right now, I mean, we have seen that machine learning, especially deep learning, has increased robustness of eye tracking devices, but we have not yet reached the accuracy that we see with classical approaches. And I think what I find interesting right now is the question whether we can actually use prior knowledge about the eye, so geometric constraints, and combine them with machine learning approaches. Because very often you have really these, let's say, black box algorithms that don't use any prior domain knowledge, and like mingling or mixing those two aspects, I think this is one of the interesting directions that I think machine learning and eye tracking will go into. So what comes to my head right now? Maybe somebody wants to comment on this or take that ball.
Yeah, I was going to say, if anybody wants to add anything, and if you're really worried about, you know, Zoom interruptions, you can also just kind of raise your hand and let us know that you want to.
I know for myself, one of the things that I'm very optimistic about, and it ties into some of the stuff that Kai had presented with that real world mapping, is to kind of take it the next step further, where we can have automated labeling of objects in the world, because we do have really good results now with the object recognition. But the, you know, as someone who's done a lot of mobile tracking with the manual annotation, it just becomes very laborious. So even just some kind of in-between method to assist with tagging of object names and things like that would be really helpful. And I know that there's a few groups that have made things like that, but I don't know if there's actually like a full solution that's out there. So I'm hoping, in the next few years, we get something that pretty much anybody can use.
Okay, if nobody else has anything to add, I'll move on to a question that is in the Q&A box right now. And I'm not sure if this is for the last talk or the keynote that we already heard, but Keenan asks, do you think ocular dominance might be the cause of the performance difference between the left and the right eyes? I think, Kai, this may be to the keynote, but I'm not
I think it was maybe to another talk, but I mean, like when it comes to the effect that I saw, as I said, it's speculation. As I said, I thought it was about say pupil visibility. There is the asymmetry in terms of pupil invisible with the eye camera being to the left. So these are obvious factors to discern whether it's actually the dominant eye effect. Correct me, but dominant eye is sometimes on the right, on the left. Why would we see such a clear asymmetry in this data? I mean, at least from the data that I've shown in my talk, I wouldn't see this as a possible explanation.
Okay. And also for the Pupil Labs group, there's a question in the Q&A chat from Jeff Pell. For the pupil, is there a special reason you decided to go with the extreme angle for the eye cameras other than keeping the system compact?
No, I think the angle was, well, Pupil Invisible really tries to sort of bridge the, or kind of bridge the two requirements of having a decent angle onto the eye and have a form factor that's invisible. And what we found is that you can actually have these extreme angles and still do gaze estimation. What we then also find is that with these extreme angles, pupillometry becomes tricky. So I think that's still, there's still this is still a challenge to essentially have decent view of the eye without optical occlusion and also without the social awkwardness and the form factor that you create then.
Another advantage that's maybe implied by the compact form factor is that the vision is less occluded, of course, with this angle. So with other eye trackers, this can often be not a huge issue, but a slight discomfort when wearing them.
There's also a question from Agostino. I'm gonna ask it. Is the Pupil Invisible spectacle lenses IR filters?
So the actual lenses that we pop in, no, they're not IR filtering at all. They're your run-of-the-mill standard glasses. So they let IR through. Even the shaded ones are IR permissive. We didn't want to make a difference in that, whether you use the shaded or the other ones. In fact, you can also operate the eye tracker, I believe, without any lenses inside. But the robustness comes from the algorithms, not from the way that we build the form factor. I know that a lot of past approaches have tried to create robustness through hardware solutions. We kind of always said that that's going to compromise usability. And we thought that we want to leverage machine learning to get the robustness there.
Okay, I have another, thank you for answering. I have another question. Kai, in his presentation, showed the unusual eye images from the eye tracker. Did you try to do some reverse engineering in your convolutional neural network to understand what features are used to track the eye? Because Yeah, they're really, I mean, that's really intriguing. Those images, if you have, let's say, the first version of Pupil Labs, you would say that you really messed up the positioning of the cameras, but still you do something with that. So have you tried?
Sorry. Yeah, I think those eye images are still intriguing to me too. It's amazing that it works. But I think, yeah, we attempted to reverse engineer and try to make sense of sort of what regions were leveraged and such. I'm not the expert on this, so I think Kai and Mark have a lot more insight. I think my like novice takeaway, kind of from looking over their shoulder, was always that it's a bit futile, that endeavor, to try to sort of make sense of the first layers or any separate layers, or it doesn't lead to much. It didn't really lead to much insight. That's what I remember, but it's been a while when we did those investigations.
Okay.
Mark, you want to say something about this?
Yeah, I mean, I think generally the whole reverse engineering of a neural network is kind of a not totally straightforward thing and how to interpret what you get out there. So I think everything needs to be taken with a grain of salt there. But I think what we could see is that more or less all the features that are visible are being used. So I mean, obviously it's stuff like pupil and iris, but then also the eyelid itself is used, which I mean kind of makes sense since upper eyelid position is like indicating the vertical eye position to a very large degree already. So yeah, it's pretty much all the features that are visible in the eye are used. Only like very skin heavy regions have seen little attention maybe from the network.
Yeah, and I think sort of the result of that is that you, no matter how terrible the circumstance, you always get some type of estimate that is, you know, I mean, we saw the numbers, but even if you have a fully occluded eye, you don't get nothing. You still get something that makes some type of some kind of sense, which sort of as a quality of an output signal or as a quality for a system, that was something that's kind of new. Because before, especially if you contrast it to pupil core, you know, very quickly you kind of get gaps in your data just because it so explicitly relies on the pupil contour, and then confidence just goes down, and then you just don't get any. And with, yeah, it's kind of the signal like that. That is a very different trade-off that the two different systems make.
Okay, thank you very much.
I'll take one question from the list that we have just to kind of mix up the topics that are going on. We had a question that came in earlier. What is the impact of eye disorders, for example, strabismus or nystagmus, on eye tracking data quality in all of the panelists' experience?
Well, I can say I worked with nystagmus patients with an iLink 1000, and there you calibrate the patient before you record them. And a fundamental problem is, I mean, a fundamental assumption is that the participant is looking at a certain dot. So if the eye is oscillating the whole time, how do you know when the participant is actually looking at the center of the dot? And so that's a fundamental problem we've been working with a bit. So that's a main challenge. So in theory, if you would need only one, most of these patients have something called a null zone. So a particular eye orientation where the nystagmus oscillations are minimized. So if you would have a system where you could do 1-point calibration in that null zone, perhaps that would be a good solution to the calibration problem in those patients.
Is there anything anybody would like to add or talk about a different oculomotor condition that anyone has experience with?
Yeah, I can chime in a little bit, and Natela, you have experiences with this too. So it's not an eye movement disorder, but also an eye disorder. So having tried to track individuals with some degree of retinal degeneration or hemianopia, which, you know, both of them end up having some issues with eye movement stability. So I think the main thing I found with that is if you do have the opportunity for manual calibration, where you can actually see the eye image and try to pace things slowly with the individual you're trying to calibrate, that tends to get slightly better results, but it's very tricky because yeah, you're dealing with individuals who don't have great eye movement control sometimes. So sometimes you just can't actually calibrate some individuals. So I was interested because I missed a little bit of Kai's initial thing on the pupil invisible. So I was curious in terms of as if we can actually have eye tracking that is completely calibration free, then this opens up this opportunity for these individuals. If we're only tracking, you know, the actual features on the eye itself and not asking the individual to look at anything. I guess there's always this issue where we don't exactly know where the retina, the fovea is with relation to the features on the, you know, the iris and the pupil. But anyway, yeah, it's tricky. It's kind of the sum of it, but I'm hoping maybe some calibration free methods might get at least something that's better than nothing.
So I actually have a question too. So if you have one eye that is lazier, if you're squinting a bit, so how does the pupil labs, what does it give you? Does it give you binocular data? Because what you normally need to do then is to patch one eye and then the other one kind of aligns during calibration, so you can actually measure the deviating eyes when you in your data later. So how does that work? What happens if you record such a patient or such a participant?
So for pupil core, which has an explicit pipeline, I mean, you have the flexibility of modifying either the code or the procedure to do monocular individual, so dual monocular calibrations, we call them. Yeah, for pupil invisible, this is kind of a different story. But I think these kinds of things, to me, it's like the pupil core system is probably more appropriate as a platform for research. I mean, with pupil invisible, we kind of make the assumption that the whole oculomotor and visual system is healthy, that you are behaving like the population average.
Do you mind if I ask a question from my former advisor, Dr. Peltz? So the robustness of the invisible is due to the large, diverse training sets, but that probably also contributes to the limit on accuracy. Would you consider an option to allow an individual to retrain a custom network if they were willing to prepare a relatively large sets?
Yeah, I think, I mean, for sure, this is super interesting. It's like one of the many avenues that can certainly be pursued and that are exciting. I think this is also why, why this, this end-to-end gaze estimation, it comes with these challenges. We have, to be honest, I mean, we've investigated these things, but I think ultimately we haven't fully gone down that path yet. But it's definitely interesting to kind of fine-tune or retrain.
Yeah, may I kind of say a bit more on that? I mean, Kai has already hinted at that there's a lot of active research going on for like somehow making general networks be person-specific, like calibrating machine learning-based networks. And I'm sure Jeff is aware of the many papers that are in there. And generally, the problem is that you really need a relatively large data set for getting a person-specific improvement. So it's not enough to collect one calibration. It's not even really enough to collect 10 calibrations, where we're talking about a bit more data. And then at some point you run into problems that you have so much person-specific data that has been recorded in limited environments and so on, that you might get better for that person within that environment, but then you lose kind of robustness to other environments. If it was recorded indoors, it might be getting worse outdoors from the customization of the network. So overall, this is a pretty complex problem, which is why so many papers are spawned from this, I think.
This would be quite hard to do on a cell phone, right? Too, because like one of the great things about this is it can run on the cell phone. But if you're talking about retraining the network, right, I don't think you could do that on a phone. Yeah.
Yeah, that's true. So the training of such networks is usually quite a lot more intensive than the execution, which already is computationally intense. So most likely something like this would need to happen with some kind of cloud solution or something like that, where you upload the calibration data.
So a question related to use of iPhones in eye tracking. Someone asks, I am very interested that eye tracking can be applied to mobile phones and have a positive impact on our daily lives. What are the possible solutions for the applications of eye tracking and handheld devices in a dynamic context, in your thinking? Is there anyone who has thoughts on mobile eye tracking or experience with it, I guess?
I mean, there are, again, machine learning based papers that try to do gaze estimation on mobile phones using the front facing camera of the phone. I think the biggest problem with doing that in practice is that the mobile phone itself is a very small object. So the target area where you want to distinguish targets on is very small. So you would need very high gaze estimation accuracy in order to really distinguish anything reasonable beyond the person's looking at the phone or not. And yeah, basically remote eye tracking that's machine learning based is quite a bit away from this level of accuracy. So I think that's probably what limits the usage on a mobile phone the most right now.
Thank you. Shifting gears a little bit, Paul asks, during Agostino's talk, we heard that depth information can be useful for gaze tracking. What about using simple world camera images to constrain improved gaze estimates, for example, using a machine learning approach? This is a question that was asked in the chat.
So is the question asking, like, if you combine the world camera information with the video from the eye cameras, and so you have like a prior on what the person is looking at, if you can improve gaze estimation?
Yeah, that's the idea. If you incorporate kind of priors about typical behaviors, you could generalize this to use of the IMU data, right? You know how the head's moving, you know how eye movements are correlated with head movements. So just going beyond using eye images alone to improve gaze estimation.
I don't have any experience doing that, but I could imagine that could be helpful. I think one, just off the top of my head, one issue you might run into is like, if you're trying to collect a data set about where people look, and now you're putting a prior on where you think people are already looking. Like, I think that, I guess to say, like, I think that for studying where people are looking, if you're trying to figure that out in the first place, you wouldn't want to do that. You wouldn't want to put that prior on it, but maybe afterwards, right? If you are just like, you already have an assumption that makes sense about where people look, then you could use that. Makes sense.
Yeah, things as simple as, you know, people tend to look at high contrast areas of the image. Can you build that in? Can you make an improvement that way?
So there's the concept of saliency, right? There's papers that have tried to use saliency predictions as a prior to where people look within the world video. And as far as I understood this, the main problem was that the saliency prediction is very task dependent. So if you would just have free viewing of images for a couple of seconds like they do in classical saliency studies, then this would probably help a lot. Their saliency is kind of well defined, but in with everyday daily activities, the saliency calculation itself is super difficult. So yeah, that's limiting there. I guess other stuff you could do is try to estimate the depth from kind of like a structure for motion approach from the single video frame. Maybe you could incorporate that. I mean, they could potentially work. I mean, I'm not sure how computationally realistic that is, since stuff like that is usually very expensive. But maybe there's information in that.
Maybe just picking up on Craig's comments he just wrote in the chat. I mean, that's probably interesting. Basically, to take the action-driven AOIs. I remember this, like when we built the very first system, that was like so notable, that the whole motor planning is such a strong signal, opening drawers and such.
I think one application of this also was, I think, for people to do online calibration. So if you can somehow from the environment with high probability figure out where people are looking, then at least for a few points you can be sure, and then you can do online recalibration of the eye tracker. It's similar.
One thing we've thought about too is for like eye motion type labeling for like smooth pursuit, for example. Like there's a pretty strong optic flow signal that matches to when you're smooth pursuing something. So that could potentially be a cue.
I think Andreas Bulling has the pursuits paper. I think that was related, yeah. I also wonder if VOR could be used, but
I think we can thank you all. The next question that we have is one of the questions that was submitted previously, and the first part of it is specific to Pupil Labs folks, and then the second half is a more broad question. Does Pupil Labs have any plans to include heuristics in the algorithm or provide an option to do so? Perhaps something that would set the depth of the object that's being calibrated. More broadly, can the panel talk about the up and downsides of providing such flexibility for model-based eye tracking?
I think I can only comment on it from a product design standpoint. I think with Pupil Core, it's definitely something that we only encourage to build and prototype. So kind of putting in some external prior or some external signal to improve. And I think you can definitely also do this Pupil Invisible after the fact. With Pupil Invisible, however, it's like the more complex you make the thing, the harder it starts to be usable and the more people sort of abuse it. And we call it voodoo logic. So yeah, you try hard to make it kind of easy to use and robust, but obviously that is super challenging. Like make something really easy to use is like really hard, because you don't really allow any. You try not to allow a lot of user input, but that means that you have to solve every problem yourself, so to speak. Yeah, so it sort of speaks a little bit. Sort of, for example, you could say like, okay, maybe there's some parallax error in the system, but we will allow the user to post hoc input the depth because they have somehow been able to estimate that externally to correct for parallax, right? And then you could build this into the system itself and engineer it into the system. But then people would have to do that. So I think we kind of opted, this as an example of something to make it more complex. We kind of opted against exploring that in Pupil Invisible. However, of course, data is all there and open. So be very, everybody's encouraged to do so. And in contrast, then Pupil Core, hey, yeah, you can for sure do that. You can for sure kind of use a depth image and intersect your gaze ray with some depth data. Instead of using the Virgin's signal, for example. Yeah, so that's just for the Pupil Labs but more broadly, I'm going to pass it on.
Does anybody want to add anything more broad or talk about their experience of integrating this into Pupil Core? I think the question was probably more specific to Pupil Core. Okay, the next question that we have is from Jacob, and he's asking, I was wondering if the panelists can talk about the limits to tracking resolution, accuracy, and precision. Clearly, there's an advantage for more pixels and getting higher precision tracking, and in Vasha's approach, but ignoring bandwidth and bulkiness, what do you think is the main limit? I'm curious, where do you think the most fruitful progress in that domain will be? Anybody?
Well, I think it's a bit of $1 million question. So there's so many things that kind of affect the estimates to some degree, and it's really difficult to tell what the main problem is. And I think for machine learning based gaze estimation, it's, I mean, as mentioned before, the obvious integration of somehow some calibration or so, because there is like visual versus optical axis offsets and so on that very clearly set a limit to how much one can do without a calibration. Yeah, but besides that, it's all kinds of things with improvements in the machine learning algorithms themselves, better data collection methods that allow you to build larger and more diverse data sets, as well as better computational budgets. I mean, that's only for the machine learning side, or for the more traditional computer vision algorithms. I don't know, maybe others have ideas there. That's, since it's such an old field, it's comparatively to the machine learning a bit more saturated, I think. Yeah, I guess these are my thoughts on that.
Well, in the eye trackers we have in the lab, in the older, for example, in the iLink 1000, the big source of inaccuracy are pupil size changes. So when the pupil size changes, even though the eyeball does not rotate, I mean, you still get the changes in gaze direction, since the pupil does not shrink or dilate symmetrically, so to speak. So in the eye trackers we use here, that's a large source of error.
Is that true that the pupil doesn't dilate symmetrically, or is that an artifact of the fact that a larger pupil is partly occluded by the top eyelid or something like that?
It's highly participant specific. So some participants have almost perfectly round and symmetric pupils the whole time, whereas some people can have very different shape of the pupil when it's constricted compared to dilated. There are definitely physiological things going on there.
Are there references about this, about individual differences in pupil symmetry?
Yeah, I can send you a lot of good papers about that. I can put them in the chat maybe.
Pardon my naivete, but that's very interesting.
Yeah.
I see that Anka has raised her hand, so perhaps we can try that mode of question asking as well.
Yeah, hi. So I noticed that Pupil Labs kind of focuses a lot more on the pupil invisible. For us in research, we are more making more use of the pupil core. So in the future, how much the company feels that it's gonna still develop and work on the pupil core part of the product?
Yeah, maybe I can speak to that briefly. Yeah, we're definitely still committed to pupil core. I don't know if we'll probably not kind of develop another hardware iteration on it, but we still have engineers working and maintaining and adding features to the software. We feel that the conceptual approach that PeopleCore takes in its hardware form factor, so the adjustable eye cameras and these things, I think they really lend themselves to make a very flexible research platform and accommodate a bunch of different form factors like what we saw today. That's always kind of a pleasure to see. But at the same time, it does make the systems, difficult to operate robustly, and we see that actually excludes a lot of research that is maybe this panel is slightly biased, so to speak, but there's a lot of people that actually would prefer to spend more time on just collecting data in different difficult environments rather than building experiment hardware or protocols or software. So yeah, we're still committed to PeopleCore, or let's say not just PeopleCore as a product, but to building open and usable and hackable research tools. But it's not going to go down on iterating on that adjustable frame situation. I think if we move forward, we'll probably still, like even with Pupil Invisible, you can actually hook up Pupil Invisible to Pupil Capture and get the eye camera images just the same. It's pretty hard to use the Pupil Capture pipeline on those images. However, let's say electrically and from standard, you can do that. We haven't restricted the access to the eye images, for example. So that ethos remains and will be there. So I think anything we build in the future is also committed to kind of being able to open up and be hackable. Obviously, with deep learning, it's a bit different than with the explicit pipelines in terms of how you can use that part. But what's also really cool and what I thought was so nice to see in the talk is that there's such an ecosystem, there's such a plethora of like different libraries and toolkits that people have built that are compatible or built around PeopleCore or have been used with data collected from PeopleCore. So it's like there's now this this world of tools and building blocks that people use and recycle and app use and whatever. And I really think that's a great asset, and that show grew kind of organically, and we value that a lot, and we want to retain that and kind of carry that over into any new product that we build. Of course, that Pupil Invisible for us, we know it's sort of a departure from what PeopleCore did in certain ways, but not in all. Yeah. I hope that answers the question a bit.
I have a question I've been sitting on for a while that I'd love to ask. I was really struck in Anka's talk by the amount of camera motion and how much that can potentially affect it, which seems to be just due to the flexibility of the stalks. So what, has anyone got any idea about what to do about that? Do we need to like put metal rods there to make it more rigid? I hear what you said about you're not going to necessarily be iterating too much on the pupil design, but are there maybe software solutions to that or other kinds of slippage? Any thoughts about what to do about camera motion?
In PeopleCore?
Sort of generally, but specifically in PeopleCore, yeah.
Sure. So whenever the relationship of the eye cameras to the scene camera changes per eye or both eyes at the same time, relationship to the scene camera, that's a problem. Because any calibration sort of makes assumptions about the geometric relationship of the camera systems. If the whole headset sort of wobbles on the face, I think we can probably work with that. So Kai has, Kai recently, a lot of Kai's work or of Kai's group actually made it into the Pupil Capture 3.0 release, which was a new 3D model that basically has multiple time scale 3D eye models and sort of instantaneously can correct for slippage. That's something that was new. That sort of addresses the problem of, but before it was like you could wear the headset, and then when you moved it, you needed a bit of time until you get a steady corrected signal again. And that now kind of the timescales of that have shifted dramatically. Yeah, we hope that sort of has been kind of visible in the community to see if that works. And we, of course, are very happy to receive any kind of feedback on that. So, but yeah, but if one of the cameras wobbles sort of in the frame, I often see that a lot of headsets kind of use the extenders or have further extenders to kind of move further out. You know, the longer the lever is, of course, the harder it gets. Sort of my very practical advice there would be to kind of try to keep the cameras close to the face, make those levers small. That should really help with you know, vibration induced deformation of the camera arms.
One thing that we ran into, we had the headband right around the head instead of the eyeglasses type on the nose, and we noticed that the band over the eyebrows, when people would move their eyebrows, this whole band is moving, right, and that moves the cameras in the same way. But yeah, that multi-temporal resolution eye model sounds like that could address it.
Yeah, as long as the whole assembly sort of is rigid but floating on the head, you have a chance. As soon as stuff starts to flex individually, it's kind of, I mean, at least from my understanding, it's a bit game over. Yeah, but that also kind of ties into, you know, when we design people core, I remember that sort of, you know, at the time when you looked at the other systems that are out there, a lot of them were kind of really big, and you strap them to the head, and it's sort of like a problem. Like, you create more weight in order to arrest the system on the subject's head, but the weight introduces inertia that, you know, that naturally creates counter movement to the head. And we try to go the other way with people core. We try to make it as lightweight as we could, because then at least it would sort of, you know, exert less forces on itself. That was the idea, and yeah.
Okay, I think we're coming up to the end of the panel and possibly this break, but it would be great for each of the panelists to kind of sum up their thoughts on track kind of the future and the now of tracking, and perhaps we can wrap up there. And we encourage all of you to use the social hour time to ask any of your really great questions there as well. Would anybody like to start?
Sure, I can start. So I guess probably I would say the thing I'm most excited about is how machine learning can help. We've seen a lot today already about how machine learning can advance eye tracking, and I'm really, really looking forward to seeing the future of that. And another thing that I thought was really cool today was the seeing the makeup included in the training set. To see how that that can be avoided as a problem. So, yeah.
Yeah, I mean, I'm totally breaking protocol, but yeah, the makeup that's kind of also nice. You know, it does not negatively affect eye tracking unless you wear crazy extensions with added mascara so much that you don't see the pupil anymore. But you know, you kind of tend to forget. It used to be a huge problem, right? You would have to ask subjects to not wear makeup or take it off, and you know, because it's so hard. And then this Kai has shown has no effect on accuracy. So that's really cool to just see certain problems. To just, you know, we kind of tend to talk about the stuff that sort of doesn't work or works or the compromise, but there's also some stuff that just kind of like gets solved. And I remember that we were excited when we saw that. So. Sorry, I'm totally breaking here.
Yeah, I was very, very excited to see the the super crazy combinations of so many different sensors and so on into a package for recording. And also we get frequent requests for, well, how can I combine eye tracking with an EEG device or stuff like that, for example. And we saw this combined with motion capture and so on. So I think there's still a lot of room for growth in combining different sensors and making it just much easier to combine them and to record them in practice. And yeah, I mean, as we saw here, there's a lot of work being done in that directions, and that's something I'm looking forward to seeing how those combinations of sensors will spark new research in the future as well.
When it comes to combination, I think I iterate what I also said in the beginning. So Pupil Labs, I mean, I've worked in this machine learning field and also in these classical pipelines. And I think it would be interesting to see what new ideas come up in the future, also to combine ideas from different parts and different types of gaze estimation algorithms. I'm really looking forward to that in the future.
Is there anything anybody else would like to add, or should we wrap up there?
Yeah, I can just add, echoing everybody else's thoughts about machine learning, adding a lot more flexibility to some of the eye tracking stuff. And I'm very optimistic too, in terms of one of the other things we didn't mention was eye movement segmentation and classification. So that's a whole other avenue that machine learning can be applied to, which will make things a lot easier, because it's still, there's really no standard other than everybody agrees that velocity threshold isn't very good, but we still use it pretty often. And then additionally too, I think the integration into virtual reality and augmented reality, we'll see a lot more where eye tracking kind of becomes this ubiquitous thing that's in, kind of consumer devices. And so will be probably more prevalent and outside of the research realm.
Maybe I'd like to take a different perspective also. Instead of waiting for this new super machine learning solutions, be a bit creative on how you design your experiments also. Usually you can find solutions around the problems you have and use the equipment available right now.
Hopefully we'll get to hear about some of this creativity in the upcoming talks. And with that, I think it's time for us to wrap up the panel. I'd like to thank all of the panelists for sharing their expertise with us and joining us. And like I said, I hope at least some of them will be available. I know the time zones are crazy. At the end for the social part of the workshop, and I look forward to connecting with all of them. Thanks very much.
Thanks so much.
Yeah,
Thank you, everyone.
Thank you.
Thanks for the great conversations and the great insights. We have our next keynote speaker, Dr. Shanidze here. I'm going to suggest maybe 1 minute, 1-2 minutes bio break if anyone wants to refresh, and then we will proceed immediately after that with the keynote talk.
Hello, everyone. You can hear me okay?
Yes, I can hear you well. Yes, I'm gonna ask if you don't mind, wait for another minute, and then I'm gonna do the introduction, and then I can take it away from there.
Sounds good. And you guys can see my slides?
I do see your slide perfectly fine. It's great to have you here.
Awesome. Thank you for having me. Hi, Vasha.
Absolutely.
Good to see you again.
Good to see you too. How's it going?
I'm well, thank you. How about you?
Pretty good, thanks.
Okay, I guess we can get started. I have the honor to introduce Dr. Shanidze. Dr. Mello is a principal research scientist at NVIDIA Research, and she leads research lead in learning and perception research group. Dr. DeBella is interested in computer vision, machine learning, human-computer interaction, and learning with limited labels or data, which is a perfect topic for eye tracking applications. At NVIDIA, she has invented technologies for self-supervised and few-shot learning, gaze, 2D and 3D head pose estimation, hand gesture recognition, among others. Her research has pushed the boundaries of HCI in cars and has led to the development of NVIDIA's innovative Drive IX product for smart AI-based automotive interfaces. She received doctoral and master's degree in electrical and computer engineering from University of Texas at Austin in 2008, 2004, respectively. Without any further ado, Dr. DeMello, please take it away.
Thank you so much, Kamran, and thank you for the invitation. So today, I'm really excited to talk to you about some of my recent research in trying to learn gaze estimation with limited amount of data or limited amount of labels. And so with that, without any further ado, let's get into it. And I just want to preface this talk by saying that I have been exploring, I primarily work on a machine learning based gaze estimation. And in the context of remote gaze tracking, that is not using any specialized sensors, but just using ordinary webcams and allowing, and observing humans using ordinary webcams and allowing them to move their heads freely and in completely unconstrained lighting environments. So that's the sort of mainstay of my research, which I've been exploring since around 5 years now. And this is very recent work in continuation along that stream of trying to use less labels and less data. So Yann LeCun famously said recently that the revolution will not be supervised. And what he meant here was specifically the AI revolution in this case. And I think I concur with that. I believe in that. Because I think that eventually, data is going to become a bottleneck in us being able to do machine learning and AI effectively. I think that in the long run, trying to continuously having to collect data and annotate is, it's just not a sustainable strategy. And at some point, data collection after a certain point has diminishing returns because you're not actually collecting, what you need is really diverse data. But if you keep collecting more of the same, it doesn't really help to improve the accuracy of your algorithm. And also like the need to have a lot of data, prevents democratization of AI technology, especially in societies or cultures where people have less ability to collect this data or sort of, the manpower, the infrastructure. And like, just as a researcher, I think to me, it always fascinates me that, as humans, we can learn with so much less data and we're really good learners. Yet, why is it that we don't have machine learning algorithms that can effectively sort of do the same things, that is learn with less data or with noisy labels and such? So this is a very rich area, and I think there's a lot to be done in this area in general in learning with limited labels and data. And in particular, I have been fascinated with trying to explore this topic in the context of gaze estimation. And so one of the first works that I'm going to talk about is this work on few-shot adaptive gaze estimation that, sorry, one second, I'm going to move my, right. So first I'm going to talk about this recent work that we did, well, not recent, from 2019 called PHASE, which is on few-shot adaptive gaze estimation. And this was work that we published at ICCV in Seoul in 2019. So the problem that we're trying to address here is the fact that we want to try to personalize gaze estimators. And, I'm sure I'm speaking to the choir here when I speak to this community, but, it's well known that, classical gaze estimation techniques where you do model fitting, the best accuracy for a particular subject is attained when you sort of do this fine tuning using some calibration samples on the subject because of the physiological differences between one subject to the other. Now, in machine learning based gaze estimation, and these are results on the MPI gaze data set, like since 2015, when the first CNN-based gaze estimation method was introduced, the accuracies have steadily improved and the gaze errors have reduced from about 6 degrees to somewhere close to 4.1 or so on the MPI gaze data set today. But these are all cross-subject accuracies in the sense that you train with a different set of subjects and then you test on a different set of subjects during inference time. So this is how the system generalizes from one set of subjects to another. However, what people have also found is that if you actually personalize these CNNs by collecting a lot of data, for example, 2,500 calibration samples of each subject, and sort of fine tune the CNNs to each particular subject, you can go down to much lower errors of 2.5 degrees. But obviously this is a lot of data to collect, calibration data to collect, and it's not feasible for every single subject. So in the machine AI community, people have also explored few-shot personalization of CNNs using 9 calibration samples or 10 calibration samples, which is much more manageable and practical. However, the red curve shows what has sort of been achieved, what was achieved, in terms of being able to do few-shot calibration with CNNs, which isn't a huge improvement in accuracy, right? So what we set out to do in this work was to try to close this gap between what you can achieve with a lot of calibration samples, but we wanted to do it using very few calibration samples, not 2,500, let's say less than 10 calibration samples. So the challenge here to keep in mind is that with 9 calibration samples, if you simply try to fine tune a CNN, it's going to overfit to those 9 samples, or so it's just going to memorize those 9 samples of that particular subject. And it will never generalize or generalize poorly to other examples of that particular subject that it encounters during test time. So because CNNs have a lot of parameters, you need a lot of data to effectively train them. So we proposed this algorithm to sort of address this problem of how to do few-shot calibration of gaze CNNs called phase. And it essentially has 2 main components. The first is we introduce a new component to learn a compact representation of gaze from input, arbitrary images, face images or eye images, unconstrained images captured with webcams. So in order to learn this really compact representation for the gaze space, we designed a specialized architecture, and it's we call it DTED, which stands for the Disentangling Transforming Encoder-Decoder Architecture. And the basic idea of this architecture is that we use it's classical encoder-decoder architecture for machine learning, except in its latent space, what we try to do is we try to disentangle and learn the factors associated with sort of the gaze of the incoming image and the head pose of the incoming image, and then all other factors, which may be lighting or any other thing that may be present in the images besides gaze and head pose. So basically, we try to learn this compact representation which disentangles. And I will not go into too much details, and you're welcome to read the paper for more details. But the basic idea is that, and this was an idea that was first introduced by Jeff Hinton, which was to learn rotation equivariant spaces in such a way that when you rotate, you physically rotate this. For example, this is the gaze code or latent space that you've learned, and it's a 3-dimensional space. And similarly, this in orange is also a head pose 3-dimensional space. When you physically rotate the space in 3 dimensions, it corresponds to a equivalent rotation of the gaze. So if you rotate this code and decode the image, that results in changing the actual, it results in creating an image with a different gaze direction, and similarly with a different head pose direction. So just to show you how it works, so after we've learned this sort of equivariant rotation latent space, we can then take an input image and we can rotate its latent code up and down and left and right, specifically the gaze code, and reconstruct an image in a different gaze direction. And similarly, we can do this for head pose as well. So this disentangling and sort of compact representation is super useful for us to be able to then calibrate our system with very few short examples of every subject. So the next part of our algorithm involves using meta-learning. So meta-learning is a framework where the idea is that it's unlike the regular training procedure that one would use in ordinary machine learning training, wherein the idea is to simply just minimize the loss on the training data set. However, in meta-learning, the idea is that you don't just learn the network itself, but you actually learn an algorithm by which you would want to train a network. So it's a way to learn a learning algorithm. And the manifestation of a learning algorithm in our case is essentially the set of weights with which you should initialize a network to train it further. So that's what we actually learn. And so in meta-learning, this is a fairly successful technique that has been used in other applications as well for few-shot learning. That is what we use in order to learn a highly adaptable gaze network, which at test time or deployment time can be fine-tuned successfully with very few calibration samples of a new subject. So in order to learn this, meta-learn this adaptable gaze learner network, we basically throw away all the other latent space codes other than that for gaze. And we essentially use simply this lower dimensional gaze as input to our meta-learning algorithm. And in the meta-learning algorithm, like I mentioned, the objective of training is slightly different in that you don't just optimize for the training loss, but what you actually optimize for is to so you first train the network. So for every subject, every time in training, you create a task, and a task comprises of a few training examples of one subject. You train the network for a few iterations with those few training examples. So for example, 9 or so. And then after training, you've updated your weights. You take the updated weights and you estimate the loss on a held out validation set from the same subject. And your goal is to actually minimize the validation loss on the held out set by backpropagating through all the update steps that you have. You maintain your computational graph in PyTorch. So you basically learn a set of weights with which you can fine-tune a network with very few examples and be able to generalize to more examples of that subject. And so once we've learned these set of weights that make our gaze network highly adaptable, at the time of deployment, we can then capture between 1 and 10 or however many few calibration samples for each subject and fine-tune our network for that particular subject to improve its accuracy for that particular subject. And so just to compare, we compared against the performance of 2 state-of-the-art existing techniques from 2019 at the time. And the 2 techniques that existed at the time were one by Zhang et al. And another by Liu et al. And the one by Zhang et al., basically what it did was it had this ridge regression step where they would just simply estimate gaze for any subject, and then the estimated values would be modified using a ridge regression step, a linear regression step at the end after the prediction had been made. And that was the blue curve here. And then in the red was another competing method where the network, it was a CNN-based method, but here the network, instead of predicting the absolute gaze value, every time it would predict a differential from a set of calibration samples. So they had like 9 calibration samples with known gaze values, and they trained a Siamese network, which would take in a pair of images and then predict the differential between them, and then like average across all the 9 calibration samples. And in green is our performance, and what you see along the x-axis is how the number of calibration samples is varying from 1 all the way to 256. And across this entire range, we did much better than the existing techniques. And then just to bring back the original picture of how we advanced the state of the art in the literature was basically this is our so if we wanted to our goal was to close this gap between calibrated and uncalibrated gaze estimation networks using very few examples. And so this is where we came in. So we bridged this gap significantly with just 9 calibration samples. And even with 3 and 1 calibration sample, we improved the accuracy of gaze estimation network significantly. And just to give you an idea for what this means in the practical sense. So, so this is showing you a demonstration of using a calibrated gaze estimation CNN versus an uncalibrated one. In red is the error that you would observe. The red dot is what, what is being estimated by the uncalibrated system. And the blue is what is being estimated by a calibrated system on a laptop distance, like a laptop working scenario. And the black is where the subject was supposed to be looking at. So for me, this is my example, and especially for people who wear eyeglasses, CNNs tend to have higher errors. So for me, it went down from 6.6 degrees before calibration to 1.7 degrees after calibration. So this, makes it a lot more feasible to be able to use CNN-based estimation techniques in, real-world scenarios where on laptops and screens, etc. Okay. So with that fun project, I'm going to move on to describing our next work, which was a follow-up work to the previous work that I described. And this is called Self-Learning Transformations for Improving Gaze and Head Redirection. And this was work we published last December at NeurIPS 2020. And so, let me just briefly describe what the goal of this project was. So the goal of this project was that, as you saw previously, in the DTED architecture that I introduced, one of the things that it was also capable of doing was gaze and head pose redirection, right? So creating images or synthesizing images in a different gaze or head pose. But as you recall, the quality of reconstruction or the image quality was not very photorealistic. And so in this work, we wanted to explore if we could sort of improve the photorealism as well as the redirection fidelity of the synthesized images more than what we had in the previous work. So we want to be able to, for example, the gaze direction and also the head pose. Another thing we considered in this particular work was we considered full faces versus just eye strips that we used in the previous work. So now what is the challenge there? So the challenge here is essentially the problem here is one of image to image translation. It's a very classical image to image, paired image to image translation, wherein you have an input image and then you have a target image from the same person with a different gaze or head pose, which is also known. And what you would hope for is that in your data set, like in an ideal data set to be able to do this task or learn this task with a CNN or machine learning technique, you would hope that between the pair of images, the only thing that changes is like the factor that you care about, for example, gaze, right? And you would want everything else to kind of stay constant. However, that's not what happens in the real world. In the real world, usually what ends up happening is that, there's other things that also change between pairs of images of the same subject. So for example, lighting might change or blurriness or shadows or whatever. So the question then is like, if you have these unconstrained data sets, which are typically captured with webcams, like how can you like learn to, control these other factors as well? So that you can map this input image to perfectly match this target image, that is, match it in terms of the extraneous factors other than gaze and head pose, like in terms of like the color and shadows and lighting and so on, as well as match the gaze and head variation. So this was the goal that we wanted to solve. And just to mention one other challenge here is that keep in mind that these extraneous factors that are kind of like confounding factors, the problem with another problem with them is that we don't have labels for them, right? They like, we don't, for the data set, we do have gaze and head pose labels, but we don't know how the lighting is quantified or the blurriness is quantified. So A, we need to discover what they are, and B, we need to be able to control them somehow so that we can change this image to perfectly match this image. And so the question then was like, how do we find them? And then how do we learn how to control them? So we came up with this method, which we called the STED, which stands for the self-transforming encoder-decoder architecture. And the idea here is that, so the main modification from the previous work that we did here was, and so before I go on to describing how this works, this is just an example of a self-learned unlabeled factor that we learned. And it kind of corresponds to broadly to lighting going from left to right of the face. So this is just discovered by the network on its own. So the main idea in this particular work is that, so if you recall, in the previous work, we were simply learning 3 embeddings. One was for sort of appearance factors, and then gaze factors, and then head pose factors. Now here too, we basically take an input image and learn a bunch of appearance factors. But in addition to that, we basically encode this image into a bunch of other factors as well. And in addition to predicting what the factor should be, we also predict like the state of the factor. So to give you a concrete example, in the case of the gaze, it would be what the embedding for gaze should be. In addition, the condition would correspond to the actual rotation values of the gaze, right? And so we just basically encode all these factors as some embedding and some state associated with it, and the state is quantified by rotation values. And so we basically make our encoder predict both of these, and we do this for a pair of images of the same subject. And what we then do is we basically, using the conditions for a target image, modify the encodings of the image, the first image, so as that we can faithfully reconstruct this image by modifying the encodings of this. So by basically doing this sort of a trick, our network is able to sort of disentangle and learn a bunch of factors that vary between these 2 images besides gaze and head pose. And then, at inference time, when we just have an input image and we want to somehow manipulate it, we simply encode it into its current embeddings and state, and then modify the state of its embeddings and reconstruct the image. So here are some results. So we compared our method for the task of gaze redirection against some of the state-of-the-art competing methods, including StarGAN and another method by He et al., which is also a GAN-based gaze redirection method. I believe it is from 2019. And so we compared against them, and in all these cases, we had much better fidelity in terms of gaze redirection as well as image quality. And we have quantitative numbers in the paper as well to demonstrate this. And also in terms of head rotation as well, we produced better results. And one other interesting aspect that we wanted to consider is that, and this is something that nobody in the literature had looked at before, which was how well can does the redirection happen such that could you synthesize or augment existing real-world data sets with the redirected versions of the images, such that you could then use these data sets, like augmented data sets, for training? And what we found, and so keep in mind that the one important thing that has to happen to enable this is that the fidelity of gaze redirection or head redirection has to be accurate. Because otherwise, you can't rely on your synthesized data to provide you with accurate data, right? So what we did was we basically tested how well we could synthesize these redirected gaze images and use them in a semi-supervised setting to learn gaze estimation. And so in orange are basically the versions of the curves where we took a small number of, varying number of labeled samples from a training data set and then augmented them. And so what we found was that when you have a very small number, this is a percentage of samples actually. So when we have less number of samples from the training data set, certainly this redirection method can help to augment that and improve gaze estimation accuracies. Okay. So with that, I'm going to launch into the last and very exciting work that I recently did with an intern, Rakshit Kothari, who I think is in the audience. So a shout out to you, Rakshit, if you're still here. So this is work we did last year on weakly supervised, physically unconstrained gaze estimation. And this is going to be presented in a couple of weeks at CVPR 2021. Okay, so without further ado, let's talk about weakly supervised gaze estimation. Okay, so the problem that we looked at in this particular work was physically unconstrained gaze estimation. So unconstrained gaze estimation is mostly for the case where the face is mostly frontal and you have a webcam like in a laptop or so looking at the subject. But recently, at MIT, there was a recent paper from MIT called Gaze 360, where they proposed this problem of physically unconstrained gaze estimation, wherein the idea is that the camera is even further out from the subject. So for example, greater than 1 meter out, observing a full body. And it could be anywhere 360 around the subject. And the idea is that you sort of want to, estimate gaze at that level. Which is the hardest among all these problems. So it's completely unconstrained. You can, so if you can't solve this problem, there are many applications, useful applications for it. So for example, you could look at, customer engagement in grocery stores, or have a surveillance camera in a room looking at, the behavior of interaction of people, or pedestrian gaze tracking, etc. But this is a very challenging problem because the camera's far out from the subject, so you can have really bad resolution. You can also be looking from 360 angles, so there can be cases where you have to rely basically on the body to make a guess about where the person might be looking, as their eyes or the face is fairly occluded. And obviously you can encounter very extreme lighting, which is also the case for frontal unconstrained gaze estimation, and not just physically unconstrained gaze estimation. So a huge challenge for physically unconstrained gaze estimation is how do you collect data for this task, right? For training such networks. Now, there are a couple of ways that people have looked at trying to collect data. One is this really nice data set called the RT-Gene data set. And what they did was they basically had people wear these eye trackers, and then they had cameras observing them. However, they ended up with images that had eye trackers in them, which they later in-painted in to remove the eye trackers from the face. There was also this recent Gaze 360 data set that I mentioned that was collected by MIT, which was published at ICCV 2019. And here, what they did was they used a Ladybug 360 camera, and they placed it in various different environments, indoors and outdoors. And they had subjects look at a known target. And then, later, because they had the depth information, they were able to sort of at the position of the subject and the 3D position of the target, they were able to compute the ground truth gaze values, right? And then there's another recent data set that was collected at ETH called the ETH X gaze data set. Here, the authors used a fairly expensive and complicated rig containing many different cameras. I believe there was 18 or 20 different cameras with a calibrated multi-view stereo system. And they had different lighting conditions, but it was all indoors. So all of these are, in my opinion, they're great ways, and they have, all these data sets are great. They have, helped us to progress unconstrained gaze estimation further. However, we wondered, like, is there a better way we can collect data, or we can leverage some existing data that you could easily find, and everybody can easily find. So our idea was this observation that, if you look at the internet has lots and lots of videos of people doing activities, humans doing activities. And there are certain activities where, gaze is fairly constrained. So for example, when people interact or two people talk to each other, there's usually this activity of looking at each other at the same time simultaneously, which means that, their gaze is going to have a certain constraint for both of them. Similarly, there's this activity of mutual gaze that happens in meetings or when multiple people are talking to each other, where multiple people look at one particular subject, right? And then there are these videos of mannequin videos on YouTube where people, I think this was a mannequin challenge that happened where people collected frozen videos of themselves. And then also when people do activities with their hands, fine grained activities, there's this constraint where people look at their hands or the object that they're manipulating. So we asked the question, like, there's all this data that can be mined for free. Can we use this data somehow to train gaze networks? In particular, for this work, we focused on the activity of looking at each other, in particular, where two people are, interacting in such a way that they're looking at each other. So what we decided to do was that we realized that it's fairly easy to show humans video clips and ask them to sort of just annotate the frames, the stretch of frames temporally where they're looking at each other or the Leo activity is happening. And it's also very easy for human annotators to just like click on the two heads of the people that are in the Leo activity, right? So we decided to use these as the weak labels and see if we can try to train gaze estimation networks with this weakly labeled Leo data. So, we designed specifically for this task, we designed this weakly supervised gaze learning algorithm. And for our algorithm, it either operates in a purely weakly supervised setting where the only data that we use to train it is the Leo data, or in a semi-supervised setting where we combine it with some little amount of data with gaze labels as well. And the network, the architecture of our network is basically a ResNet followed by static or a temporal component, depending on whether we use video data or do frame by frame analysis. And then followed by that, there's a fully connected layer, which gives you the gaze prediction. And we designed a bunch of specifically designed losses to be able to train our gaze network for the task of gaze estimation. So the green losses are the losses that we designed to be able to learn from Leo data. And then in pink are shown the losses that we specifically designed for this network to train with data that does contain gaze labels. And I'm going to briefly introduce these. So, like I mentioned, there's this physical constraint when people are doing the Leo activity, which is that they're looking at, the gaze is in equal and opposite directions. Now, the question is that enough? Like, is that enough of a constraint to simply use while training a neural network? What we found was if we just give the neural network, this in this frame as input and this frame as input and say, whatever you predict for this frame, you should predict the equal and opposite gaze for this frame, it's not enough. And it often leads the network to produce degenerate solutions that satisfy the constraint, but yet they're not physically correct. So for example, it can predict this gaze being up and this person's gaze being down. So that's not physically correct, but it is something that satisfies the equal and opposite constraint or the Leo constraint. So in order to sort of break this degeneracy while learning with this very weak constraint, learning gaze with this weak constraint, we introduced a bunch of losses to sort of also constrain these the physical setup more, which helped us to learn gaze better. So one of the first things that we did was we actually tried to estimate the overall scene's geometry. Now, in order to estimate the 3D geometry, what that basically means is we tried to estimate where the two 3D locations of the heads are relative to the camera. So in order to do this, you either need to know the dimensions of the two physical persons, or you need to know the camera matrix. But in our case, since we're using internet videos, we knew neither of those two things. And that leads to a depth ambiguity. We sort of approximate both of these things. And that leads to a depth ambiguity, which in turn leads to noise in our gaze labels. So we're essentially working in a regime where we're learning with noisy physical estimated values. So in order to sort of reduce all these noisy factors, as well as the fact that we're working with approximate data, we introduced a bunch of losses specifically to enforce Leo constraint, a Leo 3D loss, a 2D loss, a symmetric loss. And also we modified our gaze estimation loss to also predict the certainty of how confident it is of its value. And using that confidence, we also introduce a self-training or self-learning procedure where we reinforce the more confident, the confident predictions from the network, and lower the confidence, we rely less on the less confident predictions. So I'm not going into too much detail, and I encourage you to please check out the paper, which is actually posted on arXiv as well for more details. But just to give you a sense for what we got in terms of results. So this is an example where we were testing on the GAZE 360 datasets test partition. And what we found was that we used a AVA Leo dataset, which is a human activity label dataset containing the Leo activity labels. And this is showing the distribution of gaze angles that you can kind of get from the various data sets. And it's interesting that with the Leo data sets, you can get a really wide distribution of gaze angles. And additionally, since it's unconstrained data where people are interacting in different environments, you can get a lot of lighting variation as well. So it's really nice data. CMU panoptic was another data set that's collected in a CMU panoptic dome, where there's not lighting variation, but again, the activity is containing the Leo data set. And so what we basically found was that by augmenting some of the largest existing frontal gaze data sets, so gaze capture and ETHX gaze are both in the lab collected large gaze data sets. Both of these, they did not generalize well on this, very challenging GAZE 360 dataset. But when it's augmented with our AVA Leo dataset, their accuracies are nearly improved by 2x. So this is a huge, boost, and it's a great, free and cheap source of data that can be mined from the internet. Another thing we observed was that we can also use this AVA dataset, the AVA Leo dataset, to augment the GAZE 360 training dataset within dataset setting in a semi-supervised setting. So when we reduce the number of subjects that we use for training from the GAZE 360 and instead augment with AVA, we can get a huge improvement in accuracy. However, when you do use the entire GAZE 360 training set, you don't observe as much of an improvement by adding the AVA Leo, because presumably you have enough data from GAZE 360 itself. So yeah, so to summarize in this work, we showed for the first time that there's a lot of free data on the internet that can be mined and leveraged to train gaze networks if designed, if you design a proper framework to deal with the noise and the ambiguity in that data in terms of its gaze labels, which can help to improve both the cross-domain generalization of the gaze estimation task, as well as reduce the need to have collect label data as well. And so with that, I'm going to quickly wrap up because I'm running over time slightly. And I just want to mention these key takeaways from these work is that, it's really exciting for me to see that there is, there's all these ideas in machine learning of using controllable synthesis via a transforming encoder-decoder architecture to synthesize images in a controllable manner, as well as of meta learning for few shot learning. And also of mining these noisily labeled data from other sources like the internet that can be indeed applied to improving the performance of gaze estimation networks, and also to this huge problem of how do you collect gaze labeled data for training machine learning algorithms. With that, I'd like to thank you for your attention. All these works are PDFs as well as the codes. Some of the works already have code available, and the last work we will be publishing the code as well, open sourcing it. And you can also reach out to me by email or follow me on Twitter. And thank you for your attention.
Thank you very much. This is great. Thank you for the great presentation. And also, while I will be looking for questions showing up, I just want to thank you again for agreeing to provide the Best Paper Award for our workshop, and also my former mentor at NVIDIA Research, Dr. Juan Kim. So just to repeat to everyone else, we are going to provide the Best Presentation / Paper Award by the end of today. So thank you for your support. I'm looking for questions. If there's no, I'm going to start with one question about the TDED, which is a a network of encoder and decoder platform where you move to a latent space and then recreate the input, right? So how sensitive that architecture is to error and noise in the facial key point extractions. If there is a noise in terms of detecting where the key point features are, how does that actually disseminate itself to the rest of the network, which is going to be gaze estimation and then the rest of the
right. Yeah. So all of this work, yeah, the underlying pre-processing assumes that you use some key points that are estimated using off-the-shelf components or networks that indeed have error. And so in my experience, underlying errors in the gaze, in the key points, they do translate into errors in gaze estimation as well. So some of it may be, like when you're training a gaze network, some of it can manifest in the way of just a data augmentation. So what can happen is you can have, two eye patches with the same gaze value, maybe created slightly differently, shifted or so on. So in some sense, it's when you're training the downstream gaze estimation network or DTED, it can just like become the jitter in key points can kind of just become like a data augmentation that you might do even normally when training gaze networks of like shifting. But then some of it, like I have experienced, like if you do live demos and if your key points are noisy, it does translate into noise downstream in your gaze estimate, in that like your gaze estimate will be more noisy. So some things people do are like try to do common filtering and so on and so forth. But I think the bias in the errors are not, they don't translate as much as just like the noise or the variance of your estimates changing.
Thank you. And then another question, you might mention this during your talk, but I might have missed it. How, generally speaking, how do we create the ground truth data? Because in your result plots, you had it in degrees of visual angle. So I'm assuming during the data collection, there's an actual eye tracking happening for ground truth. Can you elaborate on the ground truth part of it?
Yeah. So there's a very standard procedure that a lot of researchers follow. So the basic idea for collecting ground truth is what we do typically is you show points on a computer monitor. And the assumption is that the position and orientation of the monitor with respect to the camera is known. And so the 3D positions that you're showing on the screen with respect to the camera that's viewing the subject. And then the other piece of it is that the 3D position of the eyeballs or the eye centers is usually typically computed with respect to the camera as well. And the way that that's typically done is, by detecting 2D facial key points on the image, and then using the PNP algorithm to fit a average 3D face or some kind of 3D face to the observed 2D key points to find the rotation and translation of the face. So once you know the 3D locations of the eyeballs and you know the 3D location of the target that the person is looking at, in all of them in the same camera coordinate system, you know exactly the 3D ray from each of the eyes to the point of regard. And that's how you get the ground truth calibration. Or not calibration, that's how you compute the ground truth.
Thank you. And I'm assuming the vergence signal is also very noisy because even with portable eye tracking, we have a hard time to figure out the exact vergence depth. But I'm guessing that's noisy,
so I don't think that, so most of the unconstrained gaze estimation based on webcams, they don't really consider vergence, to be honest. Right? I mean, that's
totally.
Because I mean, the degree, like the kind of errors that you're dealing with is so much higher than, close to the face eye tracking. I mean, you're like 2.5 degrees is the best you can do with calibration and so on and so forth, right? And so at that level, the assumption is, and in fact, like this data collection procedure is also not perfect, right? There's an assumption that the person is actually looking at the target, and maybe they're not exactly looking at the target, right? And so there's noise associated with that as well.
Absolutely. Yeah, thank you so much. Is there any other questions? Okay, there is one actually. For the phase system in calibration, is calibration done just once per person? Does it work well when the person is moving their head by a large amount?
Yeah, it works quite well, and it's just done once per person. So there is no need to do session calibration. You do it once. The idea of phase is that there is some person related factors. So actually, if you do a TSNE plot of gaze like embeddings of multiple people, what you find is that they have like different people are distributed in that space. I don't have images, but it's been shown multiple times. So the idea is that phase is just trying to capture some of this person-specific factors that influence gaze estimation for them once, and that's it. And it's not so much that it's capturing the variability of lighting at that particular moment, or the distance and the positioning and so on and so forth. That's not the idea. But there's just some anatomical factors of that person that influence the way the gaze should be estimated for them. That's what it captures. But yeah, no, it's and in terms of like how robust it is to rotations and so on, it's basically like what any unconstrained webcam based estimation algorithm would be, which is it allows for different lighting conditions, allows for different head rotations and so on and so forth.
Great. Okay.
And by the way, the code for phase is available publicly if anybody wants to pull and try it as well.
Sounds good. Sure. Perfect. With that, I just want to thank you again one more time for the great presentation, great talk. I guess we wrap up this part of the session now, and then we will have a break until, let's see, 12:20 Pacific time, which means it will be 9:20 p.m. Central European time. And hopefully by then we'll see everyone back again for the talk session number 3. Thank you, everyone.
Thank you.
Kamran, would you like me to talk about the social afterward real quick?
Please go ahead. Yeah. If I missed something, please go ahead.
Yeah, so if you are in Europe, we realize it's getting late, but we would like to encourage you to stick around after everything for our social hour, which is going to be in gather.town, which is a very fun interface. If you haven't used it before, you get to sort of walk around in a video game-like map, and you initiate video chats with people that are near you. I've posted the link to our Gather Town space and the password for it in the chat. We'll probably emphasize these again toward the end of the program. But just before everybody sort of takes off and goes to sleep or does their evening things, I wanted to give some encouragement to stick around and chat. You can actually, I think you may be able to enter the space now, but it's not going to be configured to accept everybody until a bit later. You might get told that the space is full. Everybody somehow tries to jump in there right now. That's all.
Sounds good. Thanks, Mark. All right, I guess so. We will see everyone in a few minutes after the break.
Okay. So it is my pleasure. Should we go ahead and start, Kamran?
Yes, please. Let's do that. Yes.
Okay, so it is my pleasure to introduce the third and penultimate session of the day, talking about data analysis in portable eye tracking. And our first talk will be on VED-BVIS, the Visual Experience Database Visualization and Interaction Tool, presented by Sanjana Ramanujam from the Department of Psychology and Neuroscience at the University of Nevada, Reno. And take it away, Sanjana.
It's actually going to be Christian, I guess, right? Christian's presenting.
Yeah.
Take it away, Christian. Sorry about that.
No worries. All right, I'm going to assume you can see my screen. You can hear me okay. If not, please stop me. So hi, everyone. My name is Christian Sinnott, and I'm really excited to speak about some of our work to create this visualization and interaction tool for use with the Visual Experience Database at the VEDB that some of my colleagues have already talked about in kind of previous sessions. Before I begin, though, I do want to express my thanks and appreciation towards the organizers for inviting me to give this talk, as well as for all their hard work to put this together. It's been great throughout the day to hear some of these talks. So to give a brief overview of what I'll talk about today concerning our software, I'll first talk a bit about the motivation behind this project, the kind of importance and need to create a joint head-eye visualization solution following the rather recent uptick in interest in kind of joint head-eye tracking methods in our field. I'll talk a bit about some of the details of our visualization software, which is still in its early stages of development, and spend some time talking about the individual modules that make up the software before showing a quick video demonstration. Finally, I'll talk a bit about future directions of development as we continue to iterate upon the software moving forward. So as we probably all know to some extent, joint head-eye tracking is a burgeoning field of research and application. It has great utility as a paradigm to answer even basic research questions relating to fields like human perception, but also has really high utility in various commercial and industrial applications. And over the last decade, we've seen a really large uptick in research using joint head-eye tracking methods. A large portion of these kinds of approaches, thankfully, have taken this open source or open access approach, sharing methods and data for the broader community to use in their own research. One of the most notable of these is the work performed by Kastner and colleagues in 2014, which detailed this early iteration of the hardware and software that would become Pupil Core and its associated software suite. More recently, we've seen this kind of open source approach to image eye segmentation by Chidar and colleagues in 2019. They used a approach utilizing deep neural networks that was really lightweight, highly accurate, and able to run in real time. The following year, Hausman and colleagues created open source plugins, as well as mounting hardware to integrate Pupil Core eye tracking with the T265 tracking camera developed by Intel, together in both Pupil Capture and Pupil Player. You can see an example of this implementation in the image here. That same year, Cathari and colleagues presented this Gaze and Wild data set, this joint head-eye data that was collected during a set of natural activities and then annotated and used to train a gaze event classifier. An important point made in some of this previous work is that it's really important to try and understand what the head is doing in order to do a good job of classifying eye movements correctly. A classic example of this that you might think of is trying to determine a smooth pursuit eye movement versus something like a VOR type eye movement. When only looking at what the eye is doing, these two movements can look very similar, but when we have information about the head, they become very distinct from each other. And while there's clearly high interest in research using these methods, as these pictures imply, this from Cathari and colleagues in 2020, many of these labs, many of this kind of research is done in this kind of DIY sense. There's this implementation of our own hardware and software in some way, whether it be entirely whole cloth or through some extensive modification of pre-existing methods and hardware. And while inevitably some of this is due to having kind of greater control over the kinds of data that we're interested in, what might also be driving this DIY approach to an extent is that despite this high level of research interest, joint head-eye trackers aren't really widely available for purchase and use off the shelf. And this is especially true when we're trying to conduct mobile head-eye tracking outside the lab. Now, to our knowledge, there's really only 2 commercially available mobile eye tracking systems that have the potential to measure head-eye movement, joint head-eye movement via IMU. One of these, talked about in the keynote this morning, is Pupil Invisible. So I won't go into too much detail here, but it does include a IMU with accelerometer and gyroscope. The other option that we found was the Tobii Pro Glasses 3, also reportedly offers joint head-eye tracking using an IMU as well. But this seems to be it. So far, there's only really 2 commercial solutions that we're able to find. And we're not sure at this point if they're even able to actually give us information about head position. If you missed a keynote earlier, this is potentially a future development for Pupil Invisible. And for Tobii, their Pro Glasses 3, the Tobii Pro Lab, their software suite for analyzing their data, is entirely closed source, so we're not really sure if it's capable of that. So another kind of motivating factor here is our own research. You know, in lieu of using one of these commercially available solutions, we've taken this DIY approach in our own work as well. And that work is the creation of the Visual Experience Database, this kind of multi-lab, multi-site effort to create a large open access data set that includes, among other data, 240 hours of joint head-eye data recorded during natural everyday behaviors. The collection of this data, of course, necessitated this custom-built headset you see on the left here. I won't go into too great of detail as that's already been covered, but we perform eye tracking through the pupil core headset, head tracking using the Intel RealSense T265, world-facing video that you see in the center here using the Flare Chameleon 3. And we also collect some positional data via GPS by a smartphone worn on the participant's body outside of this headset. And while this provides us data from more sensors that might be found in most commercial hardware, it prevents us from using the commercially available software that might come with it without some extensive modification. So to kind of sum up here, of course, collection of all of this data is a really big motivator in our current work. We have all this data and we need to start inspecting it to perform things like principled annotation, pre-processing, and even further analyses. But there isn't really a commercial solution available to analyze or visualize this data, and so it becomes necessary to start implementing one ourselves. Finally, kind of an ancillary factor here, but still important, is that collection of this data and use of this data is going to involve researchers at multiple labs and multiple skill levels. Presumably, all of these different researchers have differing levels of knowledge of coding, ocular motor behavior, and they all still need to look at this data. So creating software that is usable for even very new researchers is a high priority and really can be valuable as a training and educational tool. So next, I'll talk a bit about our software. I do want to stress that this is still very much a work in progress. It's still growing with some basic features implemented here. I'll first talk briefly about how we load the data itself into the visualizer, as well as some of the basic pre-processing that we do. Next, I'll focus on our graphing module, which serves to display time series data, as well as control playback of the entire software, before talking about the animation module that visualizes head and eye movements in a more intuitive way. I'll finish by showing a brief video demonstration of all these components for a short recording. So, as I mentioned before, we do have these multiple sensors on our custom headset. And each of these different sensors generates its own PL data file from recording. And we do need to bring these into a single common file for a visualizer to work. So we created this offline Python script that not only merges these data into a single CSV, but also synchronizes them temporally. And to do this synchronization, basically go through each sample of our head data and find the temporally nearest gaze data. We don't do any interpolation here yet, as eye and head are sampled at 200 Hertz, but interpolation might be appropriate to handle things like missing data or data of differing sample rates. Now, following this synchronization, we perform smoothing on the gaze data using a third-order Savitsky-Golay filter. And after this, data are loaded by the visualizer. So the first module that I'll talk about is this graphing module you see here on the right, which we use to plot time series data like angular head velocity, which is implemented primarily using Python's matplotlib library. Now, the purpose of this is twofold. Not only does it serve to visualize data in a way we as eye movement researchers might be familiar with, it also controls playback of the animation module that I'll describe next. Users are able to visualize head and eye data as a time series simultaneously using this module, with each colored trace in these time series representing a different axis of movement. So in this example, this top subplot here corresponds to 3 degree of freedom angular head velocity. The bottom subplot here corresponds with 2 degree of freedom gaze at the same time point. Now the current frame is indicated by this black vertical line moving across the time series. And users are able to control playback via keyboard controls, allowing the user to pause, resume, and quit playback entirely, as well as scrub forward and backward through recording. Now the data of this current frame, indicated by the line, in Python is written to a text file and fed into the next module here, the head and eye animation module. Now, as I alluded to before, this plays back recorded head and eye movements. We implemented this in Unity 2019 using free assets from the Unity Asset Store. The general purpose of this module is to recreate the head and eye movements the participant made over the course of a recording using the estimates of head and eye movements that our headset yields. Now in Unity, a single parent object, the skull, has 2 child objects, each eye, paired with it in a 3D space. Head and eye data is fed from that text file that the Python module writes, and used to animate the skull from sample to sample. The utility of something like this is that it provides a very intuitive, understandable visualization of what's going on, even to a researcher that might be really new to the field. So I'll show next this kind of short demonstration of the software and work. So with a joint head-eye visualization, you might imagine that it can become very easy to see things like compensatory head-eye movements. That's what I'm going to show here in this clip. Essentially, a participant is fixating on a near target and making a series of yaw and pitch movements to kind of fixate. Basically, this classic example of rotational VOR. So the user first starts this animation module in Unity before loading in the data with the command terminal. Data take a few moments to load in, but after that's done, this Python module appears and the animation begins. Now in the graphing module, like before, we have two different subplots, 30-degree freedom angular head velocity at the top, 2-degree freedom gaze velocity at the bottom, with each trace corresponding rotation about a different axis. Now the user is able to scrub through this recording, pause and resume playback like I mentioned before, using the keyboard, and these presses are read out in the terminal down here. Now, if we were only looking at the person's eyes, this participant's eyes, it wouldn't necessarily be clear what the participant was doing. It might just appear to be a kind of sinusoidal pattern of eye movement. But since we have head movement as well, it becomes very clear that this is a VOR eye movement. So in the future, we plan to continue to build out the functionality of our application. We do want to include all data streams that our headset seeks to capture, not just head and eye movement, but video recorded from all of our different cameras, GPS data, and even raw accelerometer and gyroscope data from the T265. Now, including these additional streams will help us perform tasks like annotation, which is aided by all this additional information, but also even more principled filtering and exclusion, which can be a novel learning opportunity for new researchers to understand the effects of different filter parameters and methods on some of the data that we plotted earlier. Finally, we're also interested in looking at data not just moment to moment, but in aggregate over an entire recording. Moving even further down the road, we want to continue to develop this tool, not just for our specific use case, but kind of to generally meet people's needs in the community. To that end, we've started considering soliciting community feedback about what their needs might be. Finally, we do want to move to a completely open source solution, as this is meant for visualizing data from a database that will ultimately be open access. So with that, I would like to thank you all for your attention, acknowledge the people that helped with this project in my lab, and the financial support received from the NSF. Thank you.
Thanks, Christian. That was a great talk. Now there's a few minutes available for questions, if anybody has any questions. I think everybody's dying to know when the skull will get a face. Perhaps is the first question.
Well, if we release in Halloween, I don't know that I can commit to a face, but yeah, we've talked about this quite a bit. Not sure yet, to be determined.
A more serious question from Craig is, are there any plans to allow automated labeling via event detection from the time series data?
Yeah, I think that would be a great application for something like this. And especially, it would be good to verify that your automation is doing what you think it is. Having a way to like manually verify any sort of automated process would be a great use case for this. So in the future, that would be a great additional application or feature for sure.
Great. Thanks so much, Christian. And with that,
there's one more question. Sorry, there's one more question. I just don't want to miss.
Sorry, I missed that.
Yeah, Scott.
Is this software for sale? I saw that it is trademarked.
It is not for sale. I'm not sure where the trademark appeared, but eventually we plan to move to a totally like open solution. So no, it's not for sale.
Thanks so much. We are running a little bit short on time. Sorry, to our next speaker. But again, I encourage everybody to reconnect and ask more great questions at the social afterwards. And our next talk will be post-processing integration and semi-automated analysis of mobile eye tracking and motion capture data obtained in immersive virtual reality environments to measure visual-modal integration. And the talk will be presented by Haley Miller with her colleagues from the University of Michigan and the University of North Texas Denton.
Thank you, Natela. Thank you. I'm going to assume everyone can see and hear correctly unless I see otherwise in the chat. The purpose of today's presentation is to share with you a novel approach to integrating and analyzing mobile eye tracking data with motion capture data. And my collaborator, Dr. Rodney Nielsen, and his students, Ian Zuratuza and Suleiman Palat from the Hilt Lab at the University of North Texas, have been absolutely instrumental in bringing this approach to fruition. So I just want to acknowledge that they are here with us in the workshop. They're not here physically with me, but if there are technical questions, you're welcome to put those in the Q&A or in the chat, and hopefully they can sort of tackle those as they arise. So in our program of work, methodological advances are really necessary to support flexibility across a variety of tasks, settings, and populations. And for the bulk of our work, autism and other neurodevelopmental conditions are the central population of interest. People with autism have known differences in visual and motor control, and these have been documented in the literature in studies of visual perception, oculomotor control, balance, and coordination. But these studies rarely incorporate simultaneous assessment of both vision and movement. So that's why this population is of particular interest to us, and that's why we like to use mobile eye tracking. The proposed mechanisms underlying vision motor differences in autism are neural structure and function, musculoskeletal structure and function, including oculomotor control, and cognitive function. And each of these domains influences the use of gaze to inform movement and motor planning. Because this is a multi-system issue, it's really critical that we have studies that directly assess vision, movement, and attention in a single paradigm simultaneously so that we can begin to understand their interplay. So to assess these mechanisms, we use a combination of tools, including mobile eye tracking, virtual reality, and full body motion capture. Objects in the virtual environment are projected onto a 180-degree wraparound screen with a 2.49 meter radius. This is part of a Motec ForceLink Karen system. The virtual environment and the motion capture system are in the same coordinate space, which makes it easy for us to compute the location of object projections on the screen, given a point of view and the screen's location. But determining where the participant's gaze intersects the screen is a more complex task, and that requires several different steps. So for the purpose of illustrating the steps and the outcomes of our post-processing approach, I'm going to present data to you from two 7-year-old boys, one with autism and one without autism, who completed a vision motor integration task battery as part of a larger study. So we're going to focus on only one of those tasks today, which you can see here in the video performed by a child with autism. The task is to watch the red target object as it rolls down an angle grid and block it at the bottom of the grid with a user-controlled object, that blue ball. That blue ball translates in the X direction based on the X coordinate of a marker that's placed on the participant's C7 vertebrae. The stimulus height is adjusted to each participant so that we can reduce the influence of head angle on visual perception and movement. Now, before we dig into the data analysis, it's important to note that there are both human and technical factors that make this type of work challenging. Since that's the theme of our workshop, we felt like it was important to bring up some of these considerations that should be made with any study of human behavior, but particularly those involving mobile eye tracking and integrated instrumentation. Some of the human factors include differences in sensory tolerance, differences in language or cognitive ability, and differences in body shape or size. And these all impact the way that we design our tasks and the level of researcher scaffolding and monitoring that's needed for participants to successfully complete this type of visuomotor battery. We've been able to use our visuomotor paradigm with people ages 7 and up across a wide range of cognitive and motor ability, including intellectually disabled individuals, nonverbal individuals. So it's possible, provided that you take these things into account in study design and you support your participants appropriately. There are also some substantial technical challenges to integrating multiple data acquisition tools. And you've heard a lot about this so far in the workshop today, but this is especially important for mobile eye tracking when you're not hardwired to your other systems. So it's challenging to temporally synchronize those data streams when you don't have that direct connection from your mobile eye tracker to your motion capture system or another piece of equipment. So the great advantage of mobile eye tracking is the ability to allow participants to be untethered and engage in more natural combinations of head, eye, and body movement. But it's important to consider that there are latency issues if you're using remote or wireless triggering, and there are potential latency issues with stimulus rendering, as well as issues related to non-uniform frame rates across devices. So it's just important to think about all of these things as we're designing our tasks, but also on the back end in the way that we process and interpret our data. Spatial alignment of coordinate systems is also a challenge. So for reasons we'll dig into in a moment, generally analysis of video-based eye tracking data requires a huge amount of time and effort when we use a traditional approach, which is manual, frame by frame. And this often yields results with low spatial precision and a high risk of human error if we're manually drawing AOIs, particularly on video-based moving images. It's just not quite as accurate as what we would hope to get spatially. So there are two common solutions to analysis. We can use a coordinate-based solution or a target-based solution. They each have strengths and limitations independently in terms of what they require and in terms of what they yield. And our approach tries to combine these two and get sort of the best of both worlds with that goal of optimizing spatiotemporal precision and automaticity. Most commercially available eye tracking systems, including the SMI glasses that we use automatic event detection based on a dispersion model with fixation as a primary event. And while this is okay as an entry point to understanding our data, it's imprecise and it doesn't really account for pursuit movement. So there are some limitations there. For that reason, we use raw spatiotemporal data in our approach. It was necessary for us to temporally align the data because our eye tracking system, as I said, isn't hardwired to the motion capture system or to the VR system. Participants just wear a little remote data collection device, which is a Samsung smartphone, in a pack on their back. And so because of latency issues, we didn't want to rely on remote triggering for this alignment. Instead, we labeled about 2,000 frames from the scene video using the label image graphical image annotation tool in Python. And we split the images into 70% train and 30% test sets. And the images contain more than 150 instances of each relevant object that was used for the alignment. We then performed transfer learning on the Inception V2 neural network, and we fine-tuned that to identify 24 objects that were relevant to our task battery. Of those 24, 12 of the objects are usable for temporal alignment specifically. So I just wanted to show you a little bit of what the object detection looks like. This is a video of the model detecting and labeling objects in the scene with the participant's gaze mapped onto the image as the yellow circle. And you can see the purple bounding boxes, the labels that go with them, and the confidence ratings that it's applying to the scene camera video. So the other piece we have to do is spatial alignment. In order to spatially align the eye tracking data with the data from the motion capture system and the virtual environment, we've got to define that relationship between the eye tracking scene camera coordinate system and the global coordinate system that the mocap and the VR share. So to do this, we had 3 markers placed on the glasses, and those are recorded by the motion capture system. We get spatial information about where the glasses are. We then know where the scene camera and its orientation are by fitting those pieces of information to the data collected. So they're unknown from scratch, but we can fit them to our data to determine their locations. To do this, we use a least squares method with the error between the projected location of virtual objects and their perceived location as computed by the location in the scene camera's image and in the learned camera model. So to compute those perceived projection locations, we apply rigid body transformation and coordinate translation to the camera model based on the location of the markers on the glasses. And this enables us to determine the point on the screen that corresponds to the center pixel in our scene camera image and the orientation of the image as well. The screen location corresponding to other pixels is then determined by the image resolution and the field of view of the scene camera. Once this model is learned, we can determine where the gaze strikes the screen based on transformation of the camera model and computing the relative gaze angle given the recorded gaze pixel. Once the participant's gaze location is known relative to the projected image, we're able to compute metrics comparing their gaze to target locations in the virtual environment. So we evaluated the object detection and temporal alignment by computing recall on the validation set after transfer learning. The object detector's recall on the test set was 97.4% for the fixation cross, which is the primary object used for temporal alignment. True positives were defined as correctly labeled bounding boxes, where the intersection with the gold standard bounds over their union was 0.75 or greater. There were at least 14 cross presentations in each visuomotor task in our battery, so the probability that we would miss too many to successfully align the data was essentially 0. Similarly, for spatial alignment, we only need a fraction of the thousands of image frames that contain target balls. So we filtered out the detections that violated the symmetry of balls. The smaller of width or height had to be at least 95% of the larger in order for the ball to be included in spatial alignment procedures. Because a 5-minute task at 30 frames per second contains about 9,000 frames, there were an ample number of images that met the criteria for inclusion. The root mean squared error on the detected objects was 3.7 pixels. But as Kai talked about earlier today, and I think somebody else mentioned it as well, that error is Gaussian. So this simple mean error is the one that's a little bit more relevant to this task, and that was 0.2 pixels in our sample. Object detection, temporal alignment, and spatial alignment were all considered part of the automated labeling procedure, and that took about 13.5 minutes for 5 minutes of video. While this is still time consuming, it doesn't require manual annotation and it runs unattended. And so it offers a substantial resource advantage over manual annotation, which would have taken several hours for that same amount of video. So our approach yields a wide array of metrics that we can use to analyze and mine spatial and temporal patterns of gaze behavior during naturalistic visuomotor tasks. In this figure, I'm going to visualize for you one such metric, which is distance to target, across a single trial for an interception task. So on the top, we have data from the typically developing participant, and I'll include little screenshots of what their eye scene camera looks like. And on the bottom, you'll see the eye movement data from the participant with autism. So here you see the participants in the early phase of the task, where they begin by fixating a cross at the top center of the grid, and then they direct their gaze to the user-controlled object and the target object to sort of get the lay of the land and figure out where they are in space. Although the average reaction time across all trials for this task was similar for both participants, the average time to target was notably lower for the typically developing participant than for the participant with autism. And that's in alignment with our prediction that the participant with autism is just less efficient at finding task relevant information in the visual world. Here you see the next phase of the task, where the participant engages in pursuit movement of the target object as it begins moving down the grid. Note here that the pursuit movement of the participant with autism is noisier than that of the typically developing participant. This is again in alignment with prior research and with our expectations, and it's consistently observed across trials. In the next phase of the task, the participant is preparing to move their body in order to intersect that target object with their user-controlled object. The typically developing participant's gaze is really locked onto that target, while the gaze of the participant with autism is sort of bouncing back and forth between their user-controlled object and the target object. They're trying to figure out where they should look. And it seems that the participant with autism is having difficulty efficiently using goal-directed gaze to extract visual information that will help inform their planning and execution of a body movement. The final phase of this trial is interception, where the typically developing participant's gaze is focused on the point of impact between the two objects in the virtual world. And here again, we see a substantial amount of noise in the data of the participant with autism, which is reflective of inefficiency in planning coordination of eye and body movements together. So the data that we use are transformed so that the gaze vector, the objects in the virtual environment, and the marker coordinates from motion capture are all using a unified coordinate system. And that enables us to identify at any given moment where a participant is looking relative to their body position and relative to objects in the virtual world. This allows us to determine whether gaze to a target location temporally precedes a goal-directed movement with a degree of efficiency and accuracy needed to support those planned motor responses, and what the spatial relationship is between gaze and targets and actions. This information is really clinically relevant for identifying visuomotor problems and also for planning and monitoring response to interventions in autism and other neurodevelopmental conditions. It's also a substantial improvement both in spatiotemporal accuracy and in resource savings over current approaches to labeling and analysis of this type of data. So we're excited to continue refining this post-processing approach, and our plan is to share pieces of code for others to use and improve as we work toward a really efficient, high-yield method for extracting meaningful information from these integrated data collection tools. I just want to acknowledge all of the folks who've been involved in this project, all of our funding sources, but most importantly, the autism community and the neurodevelopmental community who have really been a valuable asset to us in development of tasks and in gaining the access to these data. Happy to take questions now if we've got time, and you're also welcome to email me if you have questions that we can address in the time we have.
Thank you, Haley. That was a really, really cool talk. If there are any questions, I can ask probably just a few. In the meantime, I did have a question. I'm wondering, you know, the noise that you see in where the participant looks, the participant with ASD, is that related at all to the tracker noise as well, or is that entirely the noise of sort of their own behavior?
Yeah, that's a great question. So I would say I can't answer you conclusively from our current data set, but from the studies that I have done previously with both mobile and fixed head eye tracking, that is truly just noisy eye movement in general from the participant with ASD of just saccading around their world, looking for something that's relevant. And one of the conversations that you and I had offline at a previous time was whether this is just sort of fixation instability or if it's searching the visual world for something relevant. I think we're still not totally there. I will tell you in our fixation tasks, we see some of that same noise, but I really do think that for these dynamic visual tasks, part of it is I'm saccading to my ball, to the target ball, to over here and see if I can predict it, to over there, maybe it's going there. It's a visual search is what it seems to be. That's just very inefficient.
Thanks, that's very interesting. We are running short on time, so I'm gonna move on to the next talk. But again, I hope that Haley will be available for questions later. This is a
Absolutely.
really great talk.
Thanks so much.
Our next talk is Algorithmic Gaze Classification for Mobile Eye Tracking by Daniel Mueller and David Maan from Amsterdam, Netherlands. And if Daniel is available, we can go ahead and start.
Can you hear me? Can you hear me?
Yes, perfectly fine.
Okay, thanks. Well, thanks for having me. I think this talk should connect quite nicely for automated gaze classification to Haley's talk. It was really inspiring. I'm presenting you an algorithmic gaze classification for mobile eye tracking. Yeah, mobile eye tracking, Haley already said it. It's quite a laborious process when it comes to annotating mobile eye tracking data. Traditionally, I think we all have done that, manually clicking through frames and annotating gaze where the gaze was intersecting with. And this can take quite some time. It can even take experienced eye trackers more than a second to successfully classify the gaze in a frame. And our inspiration here is that over the last couple of years, the mobile eye trackers have been becoming much more accessible to a wider audience. Specifically, the commercial eye trackers of different sorts are now available for everyone. We see a lot of new users. However, the analysis of eye tracking data from mobile eye trackers has largely remained the same. Students are still clicking through the data, and we think we can do something there. Of course, there is quite a good reason behind why mobile eye tracking data is annotated manually. Of course, you have a moving frame of reference if you capture data in the real world. The quick movements, especially in movement signs or in sports, that can perturb the gaze location or add additional noise. And the partial occlusion is also very important when areas of interest are all of a sudden partially occluded. Of course, there is slippage, but that's not a point that I will address today. A really nice example of gaze annotation that illustrates these issues and these challenges is the study of human interactions. Mobile eye tracking data captured in the real world with other people in the frame. For example, here on the right side, you see an image by a study of Norbert Hagemann, where a fencing study, a fencing task was conducted. The human defender was segmented in different, here 10 areas of interest. And for example, the manual rater would have to judge whether the gaze was, for example, either on the head or on the chest, so between AOI 1 and AOI 2. And this is not always so easy. Often it requires domain knowledge of the manual rater to whether the gaze was actually located at a given frame on a certain area of interest. We believe we can actually cut down the costs of annotating mobile eye tracking data coming from studies of human interactions. And our aim was to automate the annotation process. And we have basically 2 points that I'm also going through in this presentation. First is we wanted to build an automated and also accessible annotation algorithm that people were not really in the depths of coding can also use, so that new users have a low entry barrier. And second, we wanted to validate our algorithm against the ratings of manual raters. So we basically provide a small Python package that's called Gaze Classify, and it works in 3 steps. First, the user or the researcher points to where the data is stored, the data of an eye tracking trial or a recording. It's basically the world video plus the XY gaze coordinates for each frame. Then we have a Python package that is open source. It consists of 2 main algorithms that are run or performed on the data, and afterwards the data is then exported, or the results, the annotations are exported to a CSV or JSON file, and also visualized if necessary. For the next couple of slides, I'm going to talk about the 2 algorithms, these main steps that we perform in the Gaze Classify package. So the first is pretty similar to what Haley just showed before. It's a mask RCNN segmentation of the image. It's a semantic segmentation. So we identify a semantic region on the image. Here it is on the right side, you see the area corresponding to pixels with a human shape. So human shape areas are identified, and then the gaze is compared against the human shape. So on the left side, you see the original input. On the right side, you see the segmented image. And our algorithm would then judge the gaze to lie on the human as opposed to not on the human. It's important to tell that we didn't train this algorithm. We used pre-trained weights because there are so many algorithms out there, and I think it's time that we better make use of the existing algorithms before creating new ones ourselves. On the next step, we have an instance segmentation algorithm. So sequentially, that's the second algorithm that is run. Again, we used pre-trained model. It's the open pose model coming from a 25-point COCO marker data set. On the left side, you see a gray point light display with 25 gray markers. These are the landmark properties that are identified by the algorithm. We then made a choice for the validation study to proceed with 7 of these 25 markers. They're illustrated on the left side with yellow circles. And as part of the instance segmentation, the final step was identifying the markers and then segmenting the original image to create corresponding areas of interest. And you see these on the right side. So on the right side, there are 7 areas of interest, and currently the gaze indicator, the red circle, is lying just on the orange area of interest, which would indicate that the gaze would be annotated as lying on the chest for this frame. For the validation, we used 13 judo combat sequences. The data comes from a study from Krabben and colleagues. We put a pupil core eye tracker on the head of 1 judo fighter. We captured binocular data, and we used a 5-point marker validation cross that was attached to a wall. Participant calibrated standing 2 meters from the wall, and the calibration was reperformed every 5 trials or whenever the eye tracker was touched or moved visibly. We then had 3 experienced manual raters manually annotating these 13 trials, resulting in a sample of 5,000, roughly 5,000 frames. used a resampled data set, of course, otherwise the raters would probably still be rating today. The data was resampled at 25 Hertz, and the manual raters were asked to first to report in the protocol if the gaze was directed at the body of the opposing judoka, and second, if so, which area of interest the gaze was associated to. Our areas of interest were the chest, the head, both arms, both legs, and the pelvis. And for the results, I again go through the two steps, the two main algorithms. First, the semantic algorithm. We manually clicked through all the frames, and we identified if the human was actually visible in the scene view or in the world view camera, which was the case. And the algorithm then also was asked to judge whether the human could be identified, which was the case in 97% of the frames. So the algorithm was quite good at detecting the human that was really there. What algorithm was way more conservative than the human raters was actually the judgment whether the gaze was directed at a human or not. When we look, the manual raters judged that in 87% of the frames that the gaze was actually directed at the human. The algorithm was much more conservative. And basically on the right side, there is an image showing what happened often. Because of the quick movements, the gaze would often be temporarily just outside of the body shape region. The manual raters had quite some domain knowledge and would click over this and still associate it with the body, whereas the algorithm in its initial form was more conservative and would judge this frame to be that the gaze would be outside of the body. For the instance segmentation, basically identifying the 7 areas of interest, you see in this graphic to the right, the ratings, the viewing, the percent viewing time, according to the algorithmic labels and the manual raters. You see generally the pattern holds for all raters that the gaze was most often located at the chest. So the chest was kind of a gaze anchor in this task. There are often also gaze at the head. You should just look at the manual raters 1, 2, 3 on the right side. You see that there's quite some variability between the raters when it comes to annotating these areas of interest. It's an interesting one, especially rater 2, for example, had some judgments that the gaze was directed also at the left arm, whereas the other 2 raters did not. We, of course, asked the rater afterwards why this was the case, and this was exactly one of the cases where the arm of one of the participants moved in front of the chest for a couple of frames, and rater 2 interpreted this data differently. It was quite surprising to see the variability that it was so big between the manual raters, and when we analyzed it with Krippendorf's alpha, it was at 0.61. This reliability was just as high as when we compared the algorithmic labeling against the manual raters. So basically, the reliability between the algorithmic labeling and the manual raters was not different, which was actually satisfying. When we look at the 2 algorithms, how they performed, we believe that it's a viable means to use algorithms to automate the analysis of mobile eye tracking data. There are 2 big challenges that we have to face. The first one is we don't have the domain knowledge when partial occlusions of areas of interest occur. The algorithm, in terms of the instance segmentation, worked quite okay with this. The bigger problem was with the semantic segmentation, when the shape of the human had to be considered or identified, that the algorithm performed much more conservatively. And so on the right side again, while we initially for the validation had only a binary decision made, the algorithm would say the gaze was on the body or not. In the current stage of the open source package, we actually compute the distance from the gaze center to the shape of the closest human. So in the latest version, the algorithm tells the researcher that the gaze was, here in an example, 3 pixels away from the human shape, and leaves it to the researcher to interpret, set thresholds, or model it programmatically to the domain knowledge that is required to make the algorithm more valid. And in the current stage, our project, the package gaze classify, comes in a very user-friendly way. So it's a minimal code example that can be run on Google Colab or locally on the computer with or without GPU support. I quickly run you through, it's my last slide. On line 3, an analysis object is created that holds the data and points to the models and the algorithms. On line 5, we load data in, here from a pupil invisible loader and explicitly from an exported trial folder. Of course, we're planning to support other eye trackers as well here. Currently, we just support pupil. On line 7 and 8, we run the 2 algorithms to detect human shapes and human joints. And then we finally create and annotate the data, save it to CSV or JSON, and if needed, export an additional video. It's currently in a beta version, and important thing to say is these algorithms work right now about as quick as a human writer. With GPU support, we can get it down to about 500 milliseconds a frame, or without GPU support, it's between 1 and 2 seconds per frame, which is a bit slower. Thanks a lot for having me here. I'm pretty excited to hear your questions and looking forward to hearing the next presentations as well.
Thank you, Daniel. This was a very interesting talk as well. I'm lucky to have this panel to moderate, or not panel, but session. Are there any questions? If there aren't, in the interest of time, I will move on to the next talk just because we're running a little bit behind. So if there are no questions, thanks so much, Daniel. Our last talk of this session is going to be characterizing the performance of deep neural networks for eye tracking by Arnab Biswas and colleagues from the University of Nevada, Reno.
Can you see my screen and hear me?
Yes. Yes.
Okay, thank you. So I'm Arnab, and I'm going to talk about characterizing the performance of deep neural networks for eye tracking. So as we know, with the advent of deep neural networks, we have been provided with this really powerful and robust tool to do eye tracking. And deep neural networks actually perform really well on the data set that they have been trained on. So for example, we trained a deep neural network to annotate the upper eyelids, lower eyelids, and the pupil on dataset A, and this is the performance of the deep neural network on held out data from dataset A. And the performance seems really good, right? But if we compare the performance of the deep neural network on dataset B, which is an outdoor dataset, as compared to dataset A, which was an indoor dataset, we see that our deep neural network actually doesn't perform that great, right? So the question arises that why did the deep neural network generalize better to one of the videos and not the other, despite not having labeled frames from either of these 2 videos? So in this talk, I'm going to try to address that question. So let's quickly look at our deep neural network model. So we trained our deep neural network model using 240 frames from 6 participants using eye videos from the Gaze in the Wild dataset, which is an open dataset with free moving participants with head-mounted eye tracker in an indoor setting. So these 240 frames were trained on a deep neural network based on DeepLabCut, which is a key point estimation library in Python, which is based on the ResNet 50 architecture and has been pre-trained on ImageNet. So once the deep neural network is trained, you can analyze new videos and predict the key points. And along with the key points, the model also outputs likelihoods, which is like a confidence metric for each of these key points and highly correlates with prediction error. And we will use this as a metric of model performance later on. So looking at the factors which affect generalization, deep neural network architectures, so different deep neural network architectures can learn different latent spaces, right? And that can affect model performance. And on the other hand, we have training data, and we know that if we keep on adding more and more training data, the model performance generally increases. But there's a catch to that. Like we have heard in the morning, in earlier sessions, labeling training data becomes time consuming and very cumbersome. So we want to optimize how we select our training data or label training data. So can we somehow choose training data to maximize model performance? So say you have a set of frames from which you want to label 100 frames. How do you go about selecting those 100 frames which will optimize model performance, right? So let's quickly look at the theory of generalization, which suggests that deep neural networks interpolate between training data and models fail at extrapolating to samples out of the training distribution. So what follows from this is that deep neural network performance should drop for samples far from the training distribution. And also that including labels closer to the test set in the training distribution should improve model performance. So we try this out on a model now. So first we simulated some outdoor data from the gaze in the wild data set. So the gaze in the wild data set is an indoor data set, and we wanted to challenge our deep neural network model to by predicting key points on outdoor eye videos. So we simulated outdoor data by generating additional eye videos from these 7 test subjects in the gaze in the wild data set. So we added, for example, in this example, I'll add some exposure perturbations. So we generated 4 different eye videos with increasing perturbations or increasing exposure, increasing reflection, rotation, increasing JPEG compression, and defocus blur, the kind of variability that you expect to see from outdoor videos, right? And another motive behind this was that with an increase in perturbation intensity, we expect eye videos to be increasingly farther away from the training distribution. So let's look at how we visualize the distance from the training distribution. So we simply take frames from our eye videos, run it through a ResNet 50 deep neural network, and extract the representation of the last convolutional layer. So that gives us a 10,000 dimension vector. We do that repeatedly for every frame. And then we do MDS, or multidimensional scaling, which reduces this high dimensional vector to a 2-dimensional vector. And what MDS does is it conserves the distance between the vectors in high dimensional space and reproduces the same distance in this 2-dimensional space. So in the plots, which I will show next, each dot on the scattered plot actually represents a single frame, and the distance between these dots represents the distance in high dimensional space for each of these frames. So first we project our training distribution into this MDS space. So these are the 240 frames from the training distribution. And then we look at the mean of the training data set, which is represented by the red dot shown over here. And we start projecting eye frames from the exposure perturbation into the MDS space. So this is perturbation intensity 1, and the orange arrow over here is actually pointing to the distance from the training distribution. And as we start projecting increasing perturbation intensities, increasing exposure into MDS space, we see that the orange arrow actually keeps on becoming larger, right? So that tells us that as we are increasing the perturbation intensity, the distance from the training distribution is also increasing. Now, correspondingly, we are interested in how the performance of the neural network depends on the distance from the training distribution, right? So now we're going to look at the likelihood we talked about earlier for the same frames that we have on the plot on the left. So we have the exact same frames, but now instead of representing distance, the color is actually now showing the likelihood, the performance of the deep neural network. And we see a very similar gradient for distance and performance. So that tells us that the performance of the deep neural network is actually negatively correlated with the distance from the training distribution. That is, the performance drops with an increase in distance from the training distribution, right? So we look at all the perturbations that we generated earlier. And so for exposure, JPEG artifact, etc. Here we have the likelihood as a function of cosine distance from the training distribution. So the cosine distance is basically the distance between 2 vectors, the cosine of the angle between 2 vectors in high dimensional space. And we see that as the cosine distance from the training distribution is increasing for each perturbation, the likelihood is actually dropping, right? So now that we know the distance from the training distribution determines model performance, can we somehow use it to improve the model? So first we try out fine-tuning our deep neural networks using data augmentation. So what is data augmentation? We have this initial training data set with 240 frames, and we can take every frame in this data set and add perturbations to the labels as well as the IVDU frame, right? And we can generate 4,800 labeled frames because we have like 5 different perturbations with 4 different perturbation intensities. So we have 4,800 labeled frames now, and we can select from these 4,800 labeled frames to fine-tune our deep neural network. So quickly, what we are doing, we have this deep neural network already trained on 240 frames, and we add 240 more frames to our deep neural network to fine-tune it. So we can do it 2 ways. One is using conventional augmentation. So conventional augmentation picks up 48 randomly selected frames for each perturbation from amongst the frames which we saw earlier, and adds randomly a perturbation intensity from between 1 and 4. So this way it ends up selecting 240 frames almost randomly from amongst the 4,800 frames we looked at before. On the other hand, we can use the information that distance from the training distribution actually affects model performance to smartly pick which of these 240 frames we want to fine-tune our deep neural network with. So we use something which we call the distributed augmentation. So for this, we do k-mean clustering on all the frames, that is all the 4,800 frames, to select 240 frames in ResNet space. So what this does, it prioritizes selection of frames which are distinct from the training distribution and also distinct in the space of augmentation. So say two augmentations, defocus blur and JPEG compression, are very similar to each other. So this will actually account for the similarity between augmentations as well. So now what we do is we train two different deep neural networks, one using conventional augmentation, one using distributed augmentation, and test on this held out outdoor simulated data set, right? And here we have a plot showing the increase in likelihood for the conventional augmentation case, and we see that there's about 6 to 7% increase in performance due to conventional augmentation. On the other hand, due to distributed augmentation, we have a higher performance increment, right? We have about 9 to 10%, right? So distributed augmentation is clearly helping, but not only for the overall condition. If you look at the performance increment for all perturbation, all perturbed eye videos across all perturbation strengths, the distributed augmentation is actually doing much better than conventional augmentation. So this tells us that distributed augmentation actually improves performance on simulated outdoor data. Now let's try this out on a real world outdoor data. So like my colleagues have talked earlier today about the VDB data set, which is an outdoor data set in doing mobile eye tracking. So that comes up, we have these challenges which comes with outdoor mobile eye tracking, right? So now we try the method we described earlier on this VDB data set. So this is again the MDS representation of the 4,800 frames which we talked about earlier. We call that the space of augmentations plus the training data. So we now project the new VDB dataset into the same space to look at the spatial relationship between the space of augmentation and this new dataset. And now we are going to select 240 frames to maximize performance on the VDB dataset. Now we can pause for a moment here and think about the fact that we actually have the labels of all these 4,800 frames. But just in case we did not have labels for these 4,800 frames, this would be as good as selecting frames to label and then fine tune, right? So we can think of this as a way to select frames so that we maximize performance on select frames from labeling to maximize performance on the new VDB dataset. So we do distributed augmentation as before, doing k-means on the space of augmentations to select 240 frames so that we maximize performance on this new dataset. But we also see that this new dataset has a bias with respect to the space of augmentation. It is localized somewhere, right? So what we can do is we can select 240 frames again to label, which are closest to this new dataset, the VDB dataset. On the other hand, we can also select 240 frames which are farthest away from our new dataset. So ultimately, we train 3 neural networks using these 3 different selection criteria, using positive guidance, negative guidance, and distributed augmentation. And we see, look at the increase in likelihood for these 3 different selection criteria. We see that for the positive augmentation, the increase in likelihood is almost double that of the negative augmentation, and for the distributed augmentation is somewhere in the middle. So we can label frames closer to the test data, and this can lead to better performance of deep neural networks. So I will end with a video of iVideo from the deep neural from the VDB dataset, which has the output of the negative guided augmentation and the output of the positive guided augmentation. 2 different neural networks trained using similar number of frames, but having very different performance, right? So we can intelligently select which frames to label and get a performance benefit using that, right? So that's all. Thank you for listening, and thank you to all my wonderful lab members and the PIs involved in the VDB project. Thank you.
Thank you, Arnab. That was a really interesting talk. We are kind of accumulating a little bit of a time delay. So I think we will leave the questions towards the end, and hopefully Arnab will be available both in the social hour and then also on the Q&A online. And with that, I am announcing a approximately 1 to 2 minute break and then handing the reins off to Kamran for the last session.
Sounds good. So the next session presenters, if you want to share or practice or check your slides, let me know. We can go over them while we are waiting for the break to finish.
Yeah, I wouldn't mind testing my slides.
Sure, Avi, good to see you. Go ahead.
Good to see you. Thanks so much for organizing this. It's such a great day.
It's a pleasure. So yeah, go for it. You can now share your slides and then we can check Kasia's too.
That's beautiful.
Does that look reasonable?
That looks reasonable. That looks perfect, actually.
Perfect. Thank you.
Awesome.
Let me stop hogging.
Ooh, what's going on with this funny bars? Is that just me, or can you see that too, Kamran?
I see just a black screen, basically. Oh, now I see the first slide. Perfect.
But do you see these big black boxes over it?
Yeah, you just want to.
Or like stripe box?
Right. So those are the Zoom windows, right? So if you move them somewhere or kind of minimize them, that should work perfectly fine.
Oh, that's what those are?
Yeah. So what happens is on our screen, we would see Zoom windows as black boxes, which is where you see the video feeds for other presenters.
I've been wondering about these for a year.
Oh, now I can see it. My computer was just glitching back and forth.
So this is perfect now. Now we see your slides perfectly fine.
You don't see any cover up.
Nothing at all. Yep, all good. And you're first presenter, so we can just keep going on, I guess, right? We can start now. So hopefully everyone is back from the very short break. So our last talk session is about applications. Our first presenter is Kasia Love from Smith Kettlewell. And the title of our presentation is iRobot, Calibration Challenges and Potential Solutions for Wearable Eye Tracking, excuse me, in individuals with eccentric fixation. Kasia, without any further ado, take it away, please.
Yes. Hello, my name is Cassie Love, and I'm a Harvard undergraduate working at the Eye Head Movement Lab with Dr. Natela Shanidze at the Smith Kettlewell Eye Research Institute. Along with Dr. Shanidze and Anka Vilasar, we have been working on addressing these calibration challenges and potential solutions for wearable eye tracking with eccentric fixation. So to take you, start off with important assumptions and parameters from devices. Then I will go over macular degeneration and eccentric fixation to show how these initial assumptions used in glint-free eye tracking devices complicate their use in people with non-healthy vision. To address these issues, we propose an eyeball robot that will help identify the source of calibration errors and be used to aid the future developments of calibration and tracking algorithm design that can broaden the devices used for such clinical populations. So first off, there are two important axes when it comes to eye tracking. These two are the optical and visual axis. The optical axis being defined as the center of the pupil to the center of the eye, and the visual axis being defined as the center of the pupil to the center of the fovea, which is the part of the retina with the highest resolution. And people with healthy vision use their fovea to fixate. And when it comes to eye tracking algorithms, there are several assumptions that are made. A particularly relevant one here is the fact that in normal vision, there is a small deviation between the visual axis and the optical axis, which is most of the time largely assumed to be some constant. So the goal of eye tracking is to estimate the visual axis to see where you're looking in the visual field. The eye tracker first gets the estimate of the optical axis and the curvature of the cornea to start drafting a model of your eye in the system. Next, the estimate the visual axis. To estimate this visual axis, the deviation between the two axes needs to be quantified. This can be done using fixation calibration points and the assumption that the two eye visual axes intersect on the observed surface. Having implemented these assumptions, the eye tracker can pinpoint where people are looking. But if we did this for populations where these assumptions are not valid, the eye tracker accuracy can be severely diminished. An example of such a population are those with age-related macular degeneration, AMD. AMD occurs in over 7 million individuals in the US alone, and is the most common cause of visual impairment in older adults. This impairment is due to central field loss, whereby people lose the use of the central part of the retina, their fovea. Without the central field of vision, people with AMD often develop a new eccentric reference for sight using a spot in the peripheral healthy retina. This new retinal locus is person and eye specific, and sometimes one may not develop it at all. So for an example, in normal healthy vision, one is able to see the bird, this bird in the middle, by looking directly at it. The visual axis stems from the fovea. So we have foveal viewing. But in cases like macular degeneration, when the fovea is non-functional, one has to move this part of the visual field out of the way to actually see the bird in front of them. For example, if this cartoon person was to foveate diagonally up and to the right, they would be able to see the bird by looking at it eccentrically. When talking to this person with eccentric fixation, it may seem that they're not looking straight at you since they're not foveating on you, but looking up and to the right in order to see you with like their healthy peripheral retina. This change in retinal loci changes the visual axis, and therefore the deviation between the optical and visual axis changes too. Assuming the wrong visual axis deviation by the calibration algorithm, errors in resulting calibration become more likely. So Pupil Lab eye tracking goggles are a more affordable and more compact device than those commonly used in lab settings. This tracker uses the assumption that we foveate on our visual target and the visual axes of the two eyes intersect on a surface. The eye camera records the pupil and the scene camera records the visual target. Using a transformation matrix, the 3D projections of the gaze vectors from the pupils are obtained, and then the algorithm estimates where they intersect, and this point is then projected onto a 2D scene plane as an estimated gaze point. To test if these assumptions can lead to increased errors when used with people with central field loss, we compared their calibration accuracies to age-matched controls with healthy vision. The controls had errors consistent with past work looking at pupil core accuracy. However, for people with central field loss, the errors tend to be higher and the interquartile range is much greater, showing an increased variability. This suggests a less accurate calibration, as you can see by comparing the gray control and brown MD bars in this figure to the right. We looked at two conditions, head free and head fixed, and on the y-axis we have pupil core calibration error. Participants with MD have more error in the calibration in both head restraint conditions. When it comes to the source of inaccuracies in the calibration, we've seen how the assumptions made by eye tracking algorithms may not be appropriate for the use in eccentric viewing, particularly the visual optical axis alignment. In addition, inaccuracies of the actual eye movements, as in the case of AMD, may also lead to inaccuracies in eye tracking. Since the calibration procedure is dependent on fixations, fixation during calibration could affect accuracy. As we can see in this figure to the right, when the control participant is using their fovea, you can see that there's a defined path between target points. But with eccentric viewing, we see a lot more noise and less precision in the path between target points. Also, larger fixation areas can lead to more calibration noise. In this next figure, we can see that when tasked to keep their eyes on one point, fixational areas are rather large in people with macular degeneration compared to healthy controls. The X and Y axes here on this figure are eye position and degrees of visual angle. This fixation instability would lead to inaccuracies since the calibration requires precise fixation on the calibration point. So an important question is understanding how much of the calibration error stems from the algorithm and how much of the ocular motor changes in individuals with eccentric fixation. When comparing our data to those from research standard for research industry standard, the iLink 1000. We found greater overall error using the pupil core device. However, this may be largely due to iLink's important focus on precision. When we plot pupil versus iLink calibration accuracy for MD and control groups, we again see worse errors in individuals with central field loss and eccentric fixation in both devices. And to probe this question deeper, we looked at the relationship between fixation eccentricity and calibration accuracy. We find that the larger the distance between the eccentric locus and the fovea, the fixation eccentricity, which is on the x-axis of this figure, the greater the calibration error. So how do we move forward to improve eye tracking with eccentric fixation? We'd have to pinpoint the source and reason for the errors, and then use this to improve starting assumptions to develop a more robust algorithm, and then test these new calibration algorithms for eccentric viewing. To do this, we need ground truth. We need to know the exact eye position against which we can compare the calibration and eye tracking results. So we propose a binocular robotic calibration system that allows for precise static or dynamic positioning of the eye relative to the fixation target. This device allows both central and eccentric fixation and an independent eye positioning, therefore allowing for conjugate and disconjugate eye movements. The servo's position information as well as laser positioning allows for ground truth positioning of the eyes. So here you can see the 3D CAD model for this robot. A 3D printed platform will house the servos and allows for the connection of the eyes and universal joints, and the eyes would be connected by metal push rods to the servos. And to ensure that the robot can be tracked by a model-based tracker, we designed the eyeballs to have human pupil size of 4 millimeters and a pupillary distance between them of 65 millimeters. To see mechanically where the eye is looking, laser diodes are placed within each eye. To house these diodes, however, each eyeball has a diameter of 40 millimeters, which is roughly twice the size of twice as large as an adult's eye. The robot is planned to have an ocular motor range comparable to humans in the horizontal and vertical directions. And as most eye trackers do not measure torsion, this device will not take torsion into account. And we use 3 degrees of freedom universal joint and 2 servos for each eye to move it in the horizontal and vertical direction. And to make this device widely affordable, we use low-cost 3D printed components and an Arduino-based controller. Next is the circuit diagram. I'm using a 9-volt power supply to power the servos through a parallel circuit and the Arduino Uno Rev 3 5-volt pin to power the laser diodes. And each servo has its own Arduino pin, as this allows the servos to be independent of each other for movement. And here is a quick demonstration of the eyeball robot prototype, making horizontal saccades between 2 calibration targets that are roughly 12 degrees apart. So although this prototype is promising, there are several future directions for its improvement. One is to increase the linear range of motion. We will move the axis of rotation closer to the center of the eye. Another is to mechanically build the servo to eyeball connections to where the servo angle matches the eye angle. And next is to improve the resolution of the servos. We will introduce a gear reduction using gearboxes to each servo. Through making this prototype, I've learned a lot and have a better understanding of what works and what doesn't work, and have found very simple things around the home that could help make a robot, and have a plan on how to move forward to make the robot much better. And with that, I would like to thank you all for listening and take questions. First, I would like to thank Brian Bixler for his advice on Arduino and servo control. I would like to express my special thanks to Sigma's Eye, who funded this project through their grant and native research. I would like to thank the Smith-Kettle Eye Research Institute and High Ed Movement Lab for allowing me to work on such an interesting and fun project. I would also like to thank the American Physician Sciences Association Virtual Summer Research Program for giving me the opportunity to intern at this lab. And if you have any questions, please do not hesitate to ask.
This is fantastic. Thank you, Kasia. I really enjoyed your presentation and your work. I am going to wait for a few more minutes, see if anyone has a question. Otherwise, I'm going to ask a few questions. This is great. You mentioned this is a prototype, but I was wondering whether you had the chance to characterize what range of eye movement velocities you can reproduce with the robot at this point, because it totally depends on the whole mechanical design and then the circuitry to drive those servo motors, I'm assuming, right? Did you get a chance to characterize how fast you can make the eyes rotate?
So far I have not, but I think an important step in that direction would to be sort of having a higher resolution on the servos, since as they come, the movement doesn't exactly translate as smoothly as you would want it in like normal vision. So
right. And then the other question is this you mentioned it's double the size of the human eye, right? So in comparison, how large the whole final product size is? I was just wondering.
Like the whole
the robotic eye, yeah. You had it in one of your slides, I think.
Well, like the eyeball itself is 40 millimeters to house the laser diode, but then the whole robot itself is probably around like 24 by 22 centimeters.
Yeah, just to clarify, the reason that I'm asking is because ideally you could also create a ground truth data for eye tracking applications, right? So you can kind of use an eye tracking device, create a module that looks like an eye. Of course, it's not going to have the reflections, but I was wondering whether that's a feasible direction for the future.
Yeah, I would definitely have to think about that for the software side.
Sounds good. Great, thank you so much. Let's thank our speaker one more time and then move on to the next talk by So our next speaker, Avi Eisman from UC Berkeley. She's going to talk about fixational stability as a measure for the recovery of visual function in amblyopia. Avi, by all means, please take it away.
Fantastic. Hello, everyone. Thank you so much for joining. So this project is just one example of how some of the really exciting technology we've been discussing today can be used towards more clinical applications. And to start off with, amblyopia is a developmental visual disorder that arises due to abnormal visual experience early in life. And it typically is associated with strabismus, which arises when one eye is turned either inwards or outwards. It's also associated with anisometropia, which arises due to unequal refractive error between the eyes. Now, what are some of the symptoms that we see with amblyopia? Well, reduced visual acuity in the weaker or amblyopic eye is the defining symptom of amblyopia. And it's really what clinicians are looking for when they're seeing a patient. Additionally, people with amblyopia tend to have worse stereopsis as well as abnormal ocular motor behavior. Now, here when we're comparing eye position traces as observers try to maintain fixation on a target, we can see that as compared to a normal observer and the stronger fellow eye of an observer with amblyopia, the weak amblyopic eye is showing increased instability. Now, previous work has suggested one reason we're seeing this instability is that the amblyopic eye is constantly drifting during fixation, but the corrective eye movements to bring the eye back to where it should be are error prone and actually take the eye farther away from the fixation target, which leads to this increased instability. Now, part of the reason we care so much about this instability in the amblyopic eye is that quite a bit of subsequent work has shown that visual acuity here on the x-axis and fixational stability here on the y-axis show a positive correlation for the amblyopic eye. This means that worse fixational stability while attempting to maintain fixation is associated with worse visual acuity in the amblyopic eye. Now, currently, we don't know the causality of this relationship. We don't know which is impacting the other. We just know that there is this robust relationship. Now, going back to this correlation, it's quite meaningful as reduced visual acuity in one eye is the defining symptom of amblyopia. If we can find a complementary marker to visual acuity, such as fixational stability, it gives us a nonverbal measure of the severity of amblyopia. Now, we also know that in amblyopia, treatment is most effective in young children. The earlier treatment is prescribed, the better as far as recovering visual function. If we can find a metric that can be used for nonverbal patients, like infants that can't read visual acuity charts, this could potentially lead to early interventions and better assessments of treatment efficacy. Now, if fixational stability really is a marker for the depth of amblyopia, then treatment for amblyopia should lead to changes in fixational stability. And with this current project, we really wanted to quantify whether fixational stability really does change during treatment in amblyopia and whether it can be used as a metric for the recovery of visual function. In terms of our methods, we brought in children with amblyopia as well as children without any visual disorders to be able to compare these two groups. And for our patient population, the kids with amblyopia, we focused our recruiting efforts on children currently being treated for amblyopia. And we brought in our observers 3 times over the course of 3 months. And we chose this particular duration because over 3 months of treatment, one would expect to see measurable improvements in the children currently undergoing treatment for amblyopia. During each of the sessions, we measured the visual acuity of all of our observers as well as their stereo acuity. And for our stereopsis test, we used the asteroid test, which tests a much wider range of stereo thresholds as compared to the standard clinical measures. We also measured fixational stability during each of the 3 sessions. And for this task, we asked our observers to keep their eyes as still as possible on this 1-degree smiley face at the center of the screen. And each trial was 20 seconds long. At around the halfway mark, around 10 seconds, plus or minus a few seconds, the exact timing was jittered. We did change the color of the smiley face, and we did ask our observers to hit the space bar as soon as they detected this color change. We added this task in to try and make this a little bit more engaging for our observers. And for each session, our observers completed 10 20-second trials, and we tracked eye position using the iLink 2 eye tracker. And importantly, we patched the dominant eye for all of our observers, so we were testing the non-dominant eye only. Moving on to our results, now that we've collected our data, we can actually take a look at how visual acuity changes over session. Here on the y-axis, we have visual acuity during the 3rd session, while on the x-axis, we have visual acuity in the 1st session. And our 5 control observers are shown in black, and you can see that they're all clustered quite close to the 1-to-1 unity line. Just a reminder that these observers aren't getting any sort of treatment or intervention, and we can see that their visual acuity really isn't changing over sessions. Now, in contrast, our observers with amblyopia, shown in blue and red here, all 5 observers are falling below the unity line, which suggests that all observers are showing an improvement to their visual acuity and that the treatment and interventions that they're going through are working and that we're seeing recovery of visual function. Moving on to our eye tracking data, we needed to find a way to quantify fixational stability, and we used a metric called isoline area. And in order to calculate this, we started off by estimating the probability density function of eye positions, which is shown on this plot. And we've also labeled eccentricity from 1 to 5 degrees. And this black contour that's been added corresponds to 1 standard deviation of the highest density eye position traces. And the area of this black contour in degrees squared corresponds to the isoline area. These plots here represent isoline area for a single 20-second trial for 4 different observers. And the black contour on each of these plots represents the isoline area for that observer for that trial. And in these cases, we can see that the observers with amblyopia on the top row, these observers are showing greater fixational instability than our control observers on the bottom row. Now we can start to take a look at what the overall trends look like in our data. And on the y-axis, I'm going to be showing visual acuity, while the x-axis will show fixational stability. There are going to be 3 data points per observer, 1 for each testing session. And our observers with healthy vision are going to be shown in gray, while our observers with amblyopia will be shown by blue and red. And here's what the data actually look like. And we're seeing that visual acuity and fixational stability are positively correlated. This means that people with worse visual acuity also tend to have worse fixational stability. Next, we have stereopsis here on the y-axis and fixational stability on the x-axis. And again, although the data are a bit noisy, we're seeing a positive correlation between stereopsis and fixational stability. This again means that more fixational instability is associated with worse stereopsis. And this finding, as well as the previous finding I showed, both replicate previous research. Now, ultimately, our goal is to be able to measure if fixational stability is changing in a meaningful way alongside visual acuity. And in order to quantify change, we're going to be looking at the pre-post ratio, or the ratio between the first and third session's performance. To give you an example of what this looks like, here we have an observer with amblyopia. In the first session, they had a fixational stability of around 5, while in the third session, their fixational stability was reduced to around 3. When we look at that pre-post ratio, we're seeing a value greater than 1. A value greater than 1 means that there was improvement over the sessions. Of course, if we're seeing a value of 1, that means there was no change between the first and third session. Now we can go ahead and take a look at what our data actually look like. And this next plot is showing the pre-post ratio of visual acuity on the y-axis and fixational stability on the x-axis. Now, this for us is a pretty critical finding because this is really going to suggest whether fixational stability is changing in a meaningful way over time and how these changes relate to those in visual acuity. And what we're seeing is that changes to fixational stability are positively correlated to changes to visual acuity. And what this means is that people whose fixational stability got better are also those whose visual acuity also got better. And just a reminder that we still don't know the direction of causality. We're just seeing that there is this correlation between improvements to fixational stability and visual acuity. We did want to also look at eye movements and to see how specific parameters of eye movements are changing over time. And to do this, we looked at fixational saccades, which include both large eye movements as well as micro saccades. And here I'm showing 5 seconds worth of eye position traces from 4 different observers. And I've highlighted the fixational saccades in gray so we can start to get a sense of what these eye movements look like for different observers. Here on this plot, we have the pre-post changes in visual acuity on the y-axis and changes to fixational saccade amplitude on the x-axis. And they show a positive correlation, which means that with treatment, fixational saccade amplitude is reduced during attempts to maintain fixation in the amblyopic eye. Now, we did look at a few other fixational saccade metrics, but none of these metrics were changing in a consistent way alongside the other clinical measures we were looking at, except for fixational saccade amplitude. In conclusion, our preliminary results suggest that fixational stability shows a correlation with acuity and stereopsis. And excitingly, it does look like we're seeing that changes in visual acuity are also matched by changes in fixational stability and fixational saccade amplitude. Currently, there are companies like Vivid Vision in the Bay Area developing exciting interventions for amblyopia using virtual reality. And we're also seeing eye tracking becoming cheaper, and that it's being integrated into these commercially available head-mounted displays. New interventions for amblyopia might want to consider tracking eye movements as another measure of the recovery of visual function for amblyopia. I'd like to give a big thank you to my lab, as well as colleagues I consulted with about fixational saccade identification. And I'd like to open up the floor for questions and to thank you all for your attention.
Great, thank you so much, Avi. This is great presentation. We already have one question. Is the code to calculate isoline area available?
Available.
Yeah.
I don't think so at this point. It is pretty useful, so it's something that we might want to consider putting out there. Yeah, but as of now, it's not available as far as I know.
Sounds good. I also have another question to ask you. So is it toward the end of your talk, you talk about the VR being a possible avenue for future. Is the range of these fixational instabilities detectable by the current refresh rate of eye trackings, like 120 Hertz or 200 Hertz eye tracking, or you would need to go with a very high refresh rate eye tracking to be able to detect these movements?
That's an excellent question. I think you could start to get crude estimates for some of the larger eye movements, but you're correct that some of the microsaccades wouldn't be as easily accessible by the current eye tracking technology. The hope is, though, that this is getting better over time. And I'm thinking that a more crude metric like the isoline area measure that I talked about, where you're really putting in all eye positions, that could be a good place to start with some of the limited eye tracking technology we're currently working with.
Great. And then just to clarify, your data was with iLink 1000, I'm guessing, right?
No, iLink 2.
iLink 2.
So tracking at 500 Hertz.
Gotcha. Perfect. Thank you so much. Let's thank our speaker one more time. And we should be ready to move on to our last presenter, Marcus. If you are around, okay, I can see you.
Hi, yes.
Perfect, yeah. So our last talk is by Marcus Solbach from York University, and he's gonna talk about tracking active observers in 3D visual cognitive tasks, which sounds like a very cool topic.
Thank you very much. Thank you for the introduction. A warm welcome from me. Welcome from Canada. My name is Marcus. I will be presenting today tracking active observers in 3D visual cognitive tasks. This is a system that we have built which facilitates a whole bunch of functions that were necessary in my endeavor of doing my PhD thesis with John Sossos. My talking points today are roughly structured into 4 parts. First, I will give a little background and introduction why we did all of that. Then I will present the system. We dubbed it PESAU. What that means, it is an acronym. Who would have thought? I will explain in a bit. Every system comes with some sort of software. We have all of that conglomerated in PESAU lib. And then finally, I will conclude with giving a short outlook where we want to head with the system and what we want to add to it. Let me start with giving a short quote by Bakesy, which is now over 30 years old, but still until today, very important and of course true, but a quote that should be remembered a couple times. And it reads as follows: percepts do not simply fall onto sensors as rain falls onto the ground. we do not just see, we look, which basically implies that we have some sort of active process involved when we gather information about our visual task at hand, whatever that might be. However, when we look at the current successes in computer vision specifically, often what we see is something like this, a huge data set which is used to train and also oftentimes to evaluate deep neural network systems. Don't get me wrong, successes are great, but I was wondering, how is it actually captured, all of that? And yeah, most of the times the data sets are handpicked by humans. Usually they're designed for a limited domain, for example, animals or food or places and their like. And my main point is that the camera is usually predetermined. So a human has pointed the camera at an object and triggered to take a photo, which then means that the settings were predetermined of the camera and also the viewpoints are predetermined for the system, which is then using the data set. So with other words, it is assumed that the system actually doing the visual task is an entirely passive observer. So going back to this quote here, in this publication, it is further highlighted that visual perception is an active process. It is exploratory, probing, and searching. And understanding active visual observation in humans, which is a great example because we do this every waking minute of the day and we are reasonably good at it, is actually a good source for, to see how it actually works. And this is somewhat not really understood how we solve certain problems. And what I mean with that is, what are the active processes involved? Which viewpoints do we deploy? How many? In which sequence? How do they change dependent on, for example, the complexity of an object or the appearance of an object, and so on and so forth. And ultimately, we hope that if we find some answers or at least some strategies that are involved in this whole active process, we can propose better computer vision systems, specifically looking over to the robotics side of the computer vision community. This brings me to PESAO, which kind of like tries to close this gap between how humans are doing it and the data that we need for it to understand what is happening here. PESAO stands for Psychophysical Experimental Setup for Active Observers. So you understand why I have shortened this to PESAO. It's quite a mouthful. It is designed to track active visual observation tasks. We had in mind different tasks when we started, and then we decided to make it general enough that this can be applied to different kind of tasks. What you see here in the instantiation on the right, which is just a little comic here, this is an example for the same different task. So the observer has two objects and the task is to tell if these two objects are same or different. Same different in general is done in 2D on a piece of paper. So, and then usually if it's 3D, it's a projection onto paper again. And in one of our first experiments, we were interested what actually happens when we kind of blow up these projections to actual 3D objects again, and what kind of strategies are being involved here. Very important point of PESAO was that we want to allow a natural task execution, which means not wearing a laptop in a backpack, which was kind of like the first iterations of the system, similar to talks that we have heard earlier. We want to allow free viewing, completely untethered, and as lightweight as possible, that people really can do all sorts of movements. We don't want to tell them, oh, don't do this or that. So it had to be light and untethered. Furthermore, we needed a controlled space, which also has the advantage that we actually can use a motion tracking system and also constrain certain things, what I will talk about in a little bit. And yeah, we have focused on tracking precise head motion as well as the gaze. This is a rough overview of the hardware. I will not go too much into detail. However, we have a motion tracking system consisting of 6 infrared cameras here. We're using a system by OptiTrack, but as I will explain later, this can be replaced by any system that you have at hand. This can be extended with more cameras to serve a larger tracking volume. And a wireless gaze tracking system. In this case, we use the Tobii Pro classes too. In this case, we use them in the untethered way. So we just control the classes over Wi-Fi from the workstation and store all of the data on the SD card and then post-process everything. And that's where Pisau Lib, the software conglomerate, comes into place. And also in this instantiation, we also included a webcam, or so to say, a bird's eye view camera, which observes the experimental setup from the top. Very important again, the centerpiece, which is being completely untethered. And as you can already see on the silhouette here, the motion tracking markers are actually attached right on the classes. In terms of tracking, again, these are all examples of our instantiation, but the software that we have built for the system here allows to use different amounts of sensors, different amounts of cameras for the motion tracking, and also different frequencies. But in this case, we have 120 Hertz for the head tracking in full 6D pose, which means 3 for rotation and 3 for the translation of the head. The gaze is being tracked by 50 Hertz, which is the limitation by the Tobii Pro classes to the specific version. I think they have 2 versions. We have the 50 Hertz version in our lab. And then the first person camera, which sits between the eyes right here, runs at 25 Hertz. The third person camera, as I explained earlier, the webcam, which could be any sort of camera as long as it's being recognized by OBS, which is the software to interact with live streams and video footage. And then we also track control data, which is useful to store the trial information. For example, if you run multiple trials with the same subject, as well as it allows to store observational notes. For example, if there's something that the observer sees through the camera, what that means, you will see in a second, that might be not represented directly in the data, or you want to have a little highlight, which makes it easier to dig through big data. For example, look at this specific subject here. That person did something very interesting. For this, we have also a synchronized control data stream, where you can live type some information, which being then synchronized with all of the tracking data. This basically brings then the synchronization problem up. We use a timestamp-based approach. We use the head tracking as reference frame because it has the highest frequency. And we use the lab streaming layer as an underlying framework here. Now, a couple words about the custom tracking body that we have built for the Tobii Pro classes, which remind a lot of the accessory Tobii Pro classes motion tracking that you can buy. However, we took it a level further. For example, we have made it a little larger because we did not achieve the greatest accuracy, or at least the accuracy we were looking for, depending on hairstyles and hair volumes and head decorations. So we made this whole thing a little bit wider. We also made it in a fashion that you can deassemble it in case something breaks here. You can easily then replace the certain part, so you don't have to reprint. Everything is 3D printed, everything. So you only have to replace the part that has been damaged. In our example layout, what we have built in our laboratory, we have Pisau built in a closed up area, which is closed up by blackout curtains. And then inside there, we have 2 areas, a control area, as well as a tracking area. The control area and tracking area are separated again by curtains. And within the tracking area, we have a so-called sweet spot area for tracking, which gives us about 0.4 millimeters in motion tracking accuracy. And this is just separated by a little barrier. It's a black string. And for the eye tracking accuracy, we have achieved about 1.42 error, a decreased error in visual angle, which is due to the system that we have used. These are two images from the actual setup here. In the top image, you see the tracking area in the front and the control area in the back. We have opened the blackout curtain so a little bit more light comes in there. And on the bottom, you see the control area with the control monitor here, with the motion tracking information, the web camera from which the observer can directly look into the tracking area to see what the subject is doing. And in this case, you see right now another experimenter changing for the next experiment the objects. And this brings me to the software, PISAO-LIP. PISAO-LIP is the software conglomerate for PISAO, which kind of does everything for starting from setting up the experiment, defining the variables of the experiment, to recording, interacting with the hardware, processing the data, as well as evaluating the data. All of this can be seen in the short paper, or there's also a longer version, a tech report on arXiv. I'm not going into detail here too much, but the take-home message is that we have put an emphasis on usability of this software conglomerate. It might be not the most user-friendly software to use. I'm a computer scientist myself, so it might be quite hard to understand for someone who doesn't have that background. So we have decided to have modules that have to be rewritten or adjusted for different projects because there's different tasks involved. These parts of the code are written in Python. It's a scripting language which is probably easier to pick up than, let's say, a programming language like C++. And performance relevant modules on the other side are written in C++ because of the performance. And then we also use a couple of native drivers, which just allows the best performance to interact directly with the hardware. A benefit of using LLSL, the lab streaming layer, under the hood is that this whole system can be executed either on a single machine or on a multi-machine setup, allowing, for example, large tracking volumes with a lot more tracking cameras, as well as multiple participants at the same time. In terms of the evaluation, I'm just going to give here a couple examples what we have done. On the left side, you see the bird's eye view camera, which is not really bird's eye on top, it's still on an angle. My apologies. And on the bottom, you see the live stream with the annotated gaze, what the observer is looking at. And yeah, the evaluation scripts, they allow a data preparation. For example, you want to use your tool of choice to post-process the data. You can do this by preparing your code with, or preparing the data with PISAO-LIP. You can analyze your data, and you can also visualize the data. On the right side, you see an example here. Just want to point out this example here, which is kind of the fully fledged visualization. What is PISAO-LIP capable as of today? You see here a 3D visualization with the trajectory of the person moving through the environment. And along this trajectory, you see fixation frustra colored accordingly at which object the person was looking at. Blue for object left, and then red for object right. And then randomly, we have annotated a couple of these viewing frustra with what the person has been seen, and also overlaid it with the gaze information. And this brings me to my last slide, the outlook, where we want to head with PISAO. First of all, we want to support cross-platform. Currently, the easiest way to make it run is with Windows 10. With a little bit of tinkering, probably Linux shouldn't be a big issue. However, it's not supported out of the box. You want to include more tracking options, for example, including the hands, legs, and perhaps one day a full body suit. And yeah, support more hardware vendors. Currently, we're using for motion tracking OptiTrack. Again, we're not sponsored by them at any means. It's just at the time what fitted the bill best for us. And for the classes, we use the Tobii Pro system. And if you want to find out more, you can visit this URL here. However, currently we have an issue at the department. Unfortunately, that link worked yesterday. Today, the server seems to have an issue, but yeah, keep it in mind. And that's it from my side. Thank you very much.
Thank you, Marcus. Thank you for the great presentation and detailed information about the system. Let's see if we have any questions here. We have a question from Dr. Miller. Apologies if you said this and I missed it, but are the CAD models available for the mocap handlers? We have a fixed set, but I love the option of having them modular for ease of reconfiguration / repair.
I love the term mocap antlers. That's great. If you don't mind, I want to rename this to the antlers now. Yes, we do have the CAD models. We also have 3D printable models to track objects in the scenes. All of that is available. Currently, we're working on the release of the software, and alongside the software release, the 3D printable CAD models will be available.
Great, thank you. And then regarding the software, I'm guessing it's going to be an open source software, right?
Well, the parts that we provide, yes, they will be open source. There are certain parts, for example, evaluating fixation events. These are done currently with Tobii Pro Lab, but in the long run, we also want to move over with that to open source products.
Gotcha. And then can you, maybe you mentioned this, but I probably missed that. Which part of the pipeline is in Python and which part is in C++?
Yeah, I'm just going to switch back to that slide. There we go. So the controller is done in Python, which basically takes care of controlling the actual experiment, which guides the experimenter through the entire experiment. Then a Python script is being provided that communicates wirelessly to the classes, which takes periodically timestamps, which then helps later on to make the synchronization better. So that also Python, because if you use different eye tracking solution here, you might need to put your hands on this part here. And then basically the last steps here, which is the processor, which kind of accumulates all of the information and spits out one large CSV file or a pickle file, depends on your favorite, which then can be used to evaluate the data to make nice graphs, whatever you want to do with it.
Fantastic, thank you. Let's thank our speakers if there's no more questions, which there is, and one more time, and yeah, thank you.
Yeah, thank you.
Great. Okay, so we are at the end of our sessions, roughly on time. Behind the scene, we were discussing and we were evaluating the presentation and the talks. I think Mark has a point to make. Please, by all means, Mike, go ahead. Oh, okay. So we might need probably a few more minutes just as a break, quick break, just to wrap up, prepare the final closing session slides, and then maybe get back to you guys in like 2 minutes. Does that sound good to everyone?
As my kids call it, body break.
Okay.
I'd just like to give a shout out to the organizers. This was a fantastic session today. Thank you all very much for putting this on.
Thanks to everyone. Thank you.
And for those few dozen of us who are still here, I did post the Gather Town link again. If you are still around and can hang out, we'd encourage you to just click that link and stop by. It's just as simple as going there, entering your name, and typing in the password, which is active_eyes.
I think we can return anytime if anybody, I'm not sure if anybody is taking a body break, but the organizers are done with the body break. Thank you, Mark, for organizing the social portion of the workshop. It's going to be a nice time, hopefully, to relax, but also ask hard-hitting questions. Okay, Kamran, do you want to pull up the BRM
Sure.
slide? We want to thank everybody for attending the workshop and submitting great papers for the workshop. We've been really excited to hear from all of you for the last however many months it's been. So
Absolutely, yeah. For
I think
sure, yeah.
whatever success we have is very much thanks to the people who submitted their work and presented it here today.
Definitely, I second that. It was amazing to watch so many great presentations and papers and talks, and also the panel discussions and 2 keynote talks. Before we move on to our award session, we just wanted to reemphasize that we did discuss a possible special issue journal track with Dr. Nystrom, who was here also today, just to share with the rest of the presenters today that if you are planning to extend your work and looking forward to these timelines around August, is where we are expecting to get the submissions. That's another possibility if you're interested in extending your current work.
And you'll be hearing from us about the invitations in the next week or so.
Absolutely, yeah. So the next slide is our awards. Congratulations to Kasia Love from Harvard University and Smith Carrawell, and also Natela as advisor, and also the team for winning the RTX GPU from NVIDIA, sponsored by NVIDIA. I'm pretty sure everyone enjoyed and was amazed by the work and the presentation and also the paper. All the best to you in your future work, and we'll be happy to hear from you if you're around. I think we have Anka wants to say something. 1 minute.
I think she's celebrating.
Yes. Okay. Kasia, if you're around, I don't know whether you're on our, you can unmute yourself, share what you think. We are very happy for this award.
Yes, thank you so much. I would like to thank the organizers for putting together such an amazing workshop. And thank you to my lab members for really helping me with this project.
Absolutely. It definitely was not an easy decision. Everything was very, very, very close, I should say that. Just to share with the rest of the team or the attendees, we removed the work and the submissions that were not graduate students. So only the graduate students' work or undergrad students' work were considered for this award. Next is your slide, Natela, right?
Yep. So as Kamran said, this was a very hard decision. There were really good trainee papers all around, and we struggled. And so we really want to recognize the 2 very close scores to Kasia's, and those were Vasha Dutel's work from UC Berkeley on integrating high fidelity eye, head, and world tracking in a wearable device, and Arnab Biswas's work at University of Nevada, Reno, characterizing the performance of deep neural networks for eye tracking. And these 2 papers also did very well. And we were unlucky to have an incredible set of trainee submissions. So congratulations.
Varsha, if you are around, we'd be happy to hear from you.
Hi. Yeah, thank you guys so much. It was really, really great to be here today. Thank you so much to the organizers, and I really learned a lot and had a really great time too.
Great. Arnab, do you want to say a few words, please?
Yes, thank you for organizing this great workshop, and also there were like a lot of great talks. So really enjoyed being here and presenting and talking to other people. Thank you so much.
Fantastic.
So now, as Mark has posted in the chat, if any of you are interested in attending and we hope many of you are, in attending the gather.town social time, we encourage you to do that now. We're going to close down this session and head on over to there. So see you all soon, and thanks so much for attending the workshop on behalf of myself, Kamran, and Agostino.
Oh yes, and also Agostino had a family emergency, so he said his kind words to everyone. So we should also.
We're filling in.
Yes.
Maybe don't close this because I'm not sure if people have the link elsewhere. But
okay,
drop on in together, and can we post it in Discord or something else? Is Discord still open?
Yeah, I think we can. How about this suggestion that we leave this on for another maybe 20 minutes until we probably get kicked out by the.
Sometimes cameras between the two things will interfere a bit. So if you sign on to Gather, maybe sign out of here.
Yes,
that's all.
All right. See you, everyone.